So let me start section 1.7. I will certainly not finish it today. Probably it will take the whole class, the whole next class to actually do this. Okay, so section 1.7, the precise definition of limit. So a lot of your confusion is due to the fact that we don't really have a definition yet of limit. And so this concept of a limit, the one given by Weierstrass, is the one I'm going to really show you, and Cauchy, wasn't invented until relatively recently. So suppose I have some function, y equals f of x, and I have some point A here, and well, at A, it looks like it should be L. So the limit as x approaches A of f of x is equal to L, again, if we can make f of x. So if f of x can be taken to be as close as we wish to L, by taking x is sufficiently close to, but not necessarily equal to A. So let me say this numerically. So let's look at this. So this limit here, if f can be taken as close as we wish to L. So I want to take f as close as we wish to L within epsilon. So I'm going to call this, so when I say as close as we wish, that will be denoted by some number. And I'll call that number epsilon. Why epsilon? Well, that's because that's what Weierstrass used. So it's because that's what someone used. It's the letter that someone used. So some guy used the letter epsilon, and we are going to use the letter epsilon because everyone else has used it. So we're within, oops, epsilon of this. So now, so we're within epsilon. So we're here at, so when we say epsilon, well, obviously epsilon here has to be greater than 0 because it's a distance. And so since there's a distance, I have to make this distance greater than 0. So I'm going to assume here that epsilon is greater than 0. So epsilon, I'm taking epsilon here, distance of epsilon of L. So it's either above or below L. And so a distance of epsilon from L is either, well, if I go above it, it's L plus epsilon. And if I go below it, it's L minus epsilon. And I want to take, by taking x is sufficiently close to, well, I'm going to use, since I used epsilon, I'm going to use another Greek letter, delta. So I'll use the Greek letter delta to denote that distance, the distance in x's. So the distance x's will be denoted by the letter delta. Again, I'm talking about a distance, and so I want this delta here to be greater than 0 because distances are greater than 0. And so I want to be within epsilon, both above and below A. And so if I'm delta above A, that's A plus delta. If I'm delta below A, that's A minus delta. And so this says here, I'm slowly reading this. So limit as x approaches a of f of x is equal to L, if and only if f of x can be taken as close as we wish to L, if for any epsilon greater than 0, by taking x is sufficiently close, I can find a delta greater than 0 that's as close as we wish to f of x. So that if I take any x in this interval here, then the corresponding y value is in this interval. So if I take any x in this interval here, then it will be, here, let's see, let's map up here. Actually, this is slightly bigger than this. So if I take any x here, it will be in this interval. So given any epsilon, given any interval here, if I can find an interval here where all the corresponding y values are in this interval, no matter how, and this works no matter how close we get to L, I can always find this interval. Then the limit as x approaches a of f of x is equal to L. So what this says is that, well, if you're given any open set here, and you can find an open set such that the image of this open set under this mapping F is an open subset of this given interval, then, and this works for any open set here, then the limit as x approaches a of f of x is equal to L. So let me give you the open set definition of limit. The limit as x approaches a of f of x, is equal to L if for every epsilon greater than 0, there exists a delta greater than 0, such that if the open interval a minus delta to a union the open interval a to a plus delta, then f of x is in the open interval L minus epsilon to L plus epsilon. So this says that so I can be as close as I wish within delta. So here, let's make it, oh, I guess I can't make it that small. So if for every epsilon greater than 0, I can find a delta greater than 0, such that if I take this interval, except get rid of a. So notice this interval getting rid of a is this. So take any x in this interval where and it's called a deleted neighborhood of a. So take any x in the deleted delta neighborhood of a. Then if you look at the image of that has to be within this open set. The open set L minus epsilon to L plus epsilon. So let me give this in terms of a neighborhood, which are just open sets. So this is an open set, an open neighborhood. It's a open set that contains L. And this is a deleted neighborhood of A. It's an open set, it's a neighborhood of A, except that, well, A is not in this neighborhood. You get rid of A. So let me give you some definitions. First, a deleted neighborhood of A. So, well, this will be that's an okay definition, but it's a little confusing. So we'll denote a deleted neighborhood by this little dash gives me deleted neighborhood because it's N, and a deleted neighborhood of A because it's an A here. So N sub A dash is called a deleted neighborhood of A if A is not in the deleted neighborhood of A, yet if you fill in this neighborhood with A, then, and so N neighborhood of A union the singleton A is a neighborhood of A. So it contains A. So a neighborhood of A is a set, an open set that contains A. And so if you look here, if you just fill in this hole here, then this set is an open set containing A. And so if you just fill in this point here, then this is a deleted, then this is a neighborhood of A. And so if you take away this point, this is a deleted neighborhood of A. It's a neighborhood of A, but you just took away the point A. A neighborhood of L is denoted by N sub L. It is a open set containing L. So this is a neighborhood of L. So let me give you the topological definition of limit. The limit as x approaches A of f of x is equal to L if for every neighborhood of L, there exists a deleted neighborhood of A such that f of the deleted neighborhood of A is a subset of the neighborhood of L. So this says that if for every neighborhood of L, you're in the neighborhood. You're close to L. So I'm in my neighborhood of L. There exists a deleted neighborhood of A. I'm close to A, but I'm not exactly at A. Why? Because at A, weird things can happen. So at A, I could, maybe it goes way up here, or maybe it's down here. So somehow there, maybe it's not defined here, or maybe it's defined at A way up there. But in the neighborhood, if I can find a deleted neighborhood of A such that every point in that deleted neighborhood is mapped to something inside of my neighborhood of L. And that's what this says here. This says that for every neighborhood of L, there exists a deleted neighborhood of A, such that f of the deleted neighborhood of A is a subset of the neighborhood of L. And lastly, of course, we're going to, for tomorrow, I guess I'm going to redo this because you have to hear this 50 times before you understand what I'm saying. the epsilon delta definition of limit. So rather than calling these, neighborhoods and all this, let me just put numbers here. And we'll call them epsilons and deltas. So the limit as x approaches a of f of x is equal to L if for every epsilon greater than 0, there exists a delta greater than 0, such that the absolute value of x minus a being between 0 and delta implies that the absolute value of f of x minus L is less than epsilon. On the precise definition of the limit. So we want to somehow define the concept of a limit. And the concept of the limit was that as I keep getting closer and closer to some point A, I want to figure out, well, what do the y values here approach? And so as I get closer and closer to A here, what do the corresponding y values approach? And so this is the concept of a limit. Note that I do not care what actually happens at A. I don't care what happens here. I don't care that at A, it's not necessarily equal to L. I just care that as x approaches A, my y values get closer and closer to L. So we wanted to make this into some sort of precise idea. And so we wanted that I can be as close as I wish, if I can be as close as I wish to L, by taking values of x sufficiently close, but not necessarily equal to A, then the limit as x approaches A of f of x is equal to that value L. So the limit as x approaches A of f of x is equal to L if for every epsilon greater than 0, there is a delta greater than 0, such that if x is in the union of the two open intervals from A minus delta to A union the open interval from A to A plus delta, then f of x is in the open interval from L minus epsilon to L plus epsilon, which is just a restatement of this idea that I can be as close as if I can be as close as I wish to L, if my y values can be as close as I wish to L by taking x's sufficiently close to, but not equal to, A. Then the limit as x approaches A of f of x is equal to L. Recall that this is called a deleted neighborhood of A. It is an open, so it's an open set, a neighborhood of A. Let's first say a neighborhood of L. A neighborhood of L is an open set that contains the value L. An open set of A neighborhood of A, is an open set of A that contains A. A deleted neighborhood of A is a neighborhood of A that does not contain A. So it's just a neighborhood of A where I have taken away the singleton A. And so a deleted neighborhood what happened there? And so a deleted neighborhood of A is just a neighborhood of A where I've taken away the singleton A. So I've just taken away that one point A. And that is a deleted neighborhood of A. And so it's some open set containing A. And then I take away the point A. And so it's what it looks like here. It is this open set of A, this open set containing A, where I've just taken out this one point A here, because it could be that there's a hole at A, or maybe not a hole at A. Who cares? I don't care what happens at A. And so I'm not even going to, I won't let my mind even think about it. I'll just sort of get rid of it because it's something that I don't care about. Okay, so that's a deleted neighborhood of A. So, oops. Let me just drop this. So, let me give you another definition of the limit. The limit as x approaches A of f of x is equal to L if for every neighborhood of L, there exists a deleted neighborhood of A such that f of the deleted neighborhood of A is a subset of the neighborhood of L. Again, meaning that if I'm in any neighborhood of L, I can find, so given any neighborhood of L, I can find a neighborhood of A, and I don't really care what happens at A, so I'll take a deleted neighborhood of A, such that if I take any point in this deleted neighborhood and look at how F maps it, then I am still in this neighborhood of L. Okay. And this is just about where we ended last time. The epsilon delta definition of a limit. So this is something that's going to be very important. So you must memorize this because we'll be using it throughout this chapter and you will be tested on it. The limit as x approaches A of f of x is equal to L if for every epsilon greater than 0, there exists a delta greater than 0 such that if x minus A in absolute value is between 0 and delta, then the absolute value of f of x minus L is less than epsilon. Let me restate this as something involving tolerances. So let me tell you what a tolerance is. So f of x has a tolerance of epsilon, an epsilon tolerance at L, means that the point x, f of x, lies between the horizontal lines y equaling L plus epsilon and y equaling L minus epsilon. So f of x has a epsilon tolerance of L if every point x, f of x, lies between the horizontal lines y equal L plus epsilon and y equal L minus epsilon. And so let's look at this picture here. So this is the function y equal f of x. And this is the point L. Then we will be in a epsilon tolerance of L if, so my y values are in an epsilon tolerance of L if all of my y values lie between L minus epsilon and L plus epsilon. So if all my y values are in this strip here. X has a delta tolerance of A if, well, X is between A minus delta and A plus delta. Actually, maybe I should. Let's see if I can maybe make it orange. So if not necessarily here. So your x's, so basically you're in this little box with, well, you've gotten rid of the line in the middle here. So you're somehow in this rectangle. If f of x is your y values are in this epsilon tolerance of L, and your x's are in a delta tolerance of A. Note here that it doesn't matter what happens along this strip here, this line that contains x values equal to A. So we're getting rid of these values here where x is equal to A, because I only want to be close to, but not necessarily equal to A. And so, again, I want my y values to be within epsilon of L, and my x values to be within delta of A, but not necessarily equal to A. So this is a epsilon tolerance at L and a delta tolerance at A. Note, remember, that the delta tolerance at A does not include the value x equal A. So now let me restate the limit definition yet again. So the tolerance definition of a limit. The limit x approaches A if f of x is equal to L means that for every epsilon tolerance of L, there exists a delta tolerance at A such that if x is in the epsilon, if x is in the delta tolerance of A, then f of x is in the epsilon tolerance at L. Which, if you notice, that's just a restatement exactly of this epsilon delta definition. It's just in terms now of something visual that you can see, these tolerances. So let's recall that n sub a is called a neighborhood of a if n sub a is an open set with a in this neighborhood of a. N sub a with a little dash above it is defined as, in the neighborhood n sub a, take away the singleton a. This is called a deleted neighborhood of L. N sub a with the superscript of L is called a left neighborhood of A if it is an open set with A as its least upper bound. An upper bound, so suppose you have a set here. Well, maybe I should actually draw a set. Suppose I have a set here. And maybe a set including some single numbers and maybe a continuum of numbers. Then a upper bound is something that's bigger. So that's an upper bound. Here's another upper bound. Here's another upper bound. What's the least upper bound? Well, it's the one that's small. That's no longer an upper bound. So if you take something that's less than it, it won't be an upper bound. So that's the least upper bound. It's the smallest of the upper bounds. And so, of course, there's also a lower bound. So this is a lower bound. So these are the lower bounds. And while this is the greatest lower bound, if you take anything bigger, it will no longer be a lower bound. Now, it could be that, let's say, oops. Let's say that we have this interval here. It could be that, here's an upper bound, here's an upper bound. Here's the least upper bound, the least upper bound. It could be that the least upper bound is not actually in the set, because maybe this is an open interval. So it could be that the upper bounds may not actually be in the set. So your least upper bound may not be in your set. So that's why, I don't say the biggest number, because it could not, it may be that you don't have a biggest number in the set. But it's the thing that would be a biggest number if they did have a biggest number. So that's the least upper bound. It's the thing that you think should be the largest number, but just because of some possible technicalities, it might not actually be the largest number. Okay, so and actually, I guess I didn't give this definition, even though, well, let me restate this now that I've told you what least upper bounds and greatest lower bounds are. So n sub a superscript L is called a left neighborhood of A if it's an open set with A as its least upper bound. N sub A superscript R is called a right neighborhood of A if it is an open set with A as its greatest lower bound. So let F be defined on some deleted neighborhood of A, then the limit as x approaches A of f of x is equal to L is defined as, for every epsilon greater than 0, there exists a delta greater than 0 such that x minus a in absolute value is between 0 and delta, implies that f of x minus L in absolute value is less than epsilon. Let f be a function defined on some deleted neighborhood of L of A. Then the limit as x approaches A of f of x is equal to L is defined as for every neighborhood L, there exists a neighborhood, a deleted neighborhood of A such that f of the deleted neighborhood at A is a subset of the neighborhood of L. Okay, so these are the precise definitions of the limit. We will probably use this precise definition of a limit in the following. So, first theorem is, well, this is all nice and fine, but is the limit unique? So, I mean, I'm talking about a limit as if I knew that the limit was well-defined. Well, is it well-defined? Am I somehow giving you something and, well, doesn't this definition maybe gives me 12 different limits or an infinite number of limits? Well, the answer is, well, no, it doesn't. Actually, it gives you a unique definition of a limit. And so that's what this theorem says. So theorem, the uniqueness of a limit. And so, oops. There it is. I have to turn these off. Okay, so not right now, but I'll turn these off. Okay, so the limit as x approaches A of f of x is equal to L, and the limit as x approaches A of f of x equal M implies that L is equal to M. So this first statement says that the limit exists if it's equal to something, a number. Then when I write this statement down, the implication is that the limit exists. And not only does the limit exist, but it's equal to this value. So this statement here says that f of x has a limit as x approaches A, and the limit as x approaches A is equal to L. Or maybe it's also equal to M. Well, they're always going to be the same number. So it turns out that they're actually not different numbers. The limit here is actually unique. So, well, let's try to find a contradiction. Let's try to see what happens if this state, so this is, I say that this holds. Well, what if this doesn't hold? If this doesn't hold, then I'll have to see if I get a contradiction to these two limits existing. If I do, then I've shown this. So if I can show that if this is false, that implies that one of these two statements here is incorrect. At least one of these statements is incorrect. Then this must be a true statement. So let's suppose that, well, L is not equal to, oh, and I guess I should say this. This here, PF, means I'm starting the proof. This here, QED, means I'm done with a proof. Why do I do that? Because students are unable at many times to figure out where does the theorem end? Where does the theorem begin or end? Well, the theorem begins here where it says theorem. The theorem ends here when it says proof. Next, where does the proof begin and where does it end? Well, the proof begins when it says PF, and the proof ends when it says QED. So these are helps for the student, for the reader, to figure out what the heck is going on. And so PF means I'm starting the proof, QED means I'm done with the proof. Let's see, this is for quod erat demonstratum. It's a Latin mistranslation of a Greek term, which in Latin it means that thus it has been demonstrated. So I've shown the following, the above statement. So I'm done with the proof. Oh, and this symbol here means basically it's a railroad crossing. And so this means problem. So you never want to go across a railroad crossing when a train is crossing also. And so that means danger, danger, something's wrong. It means the following statement is an error. And so if you write this symbol here, it means that we have arrived at a contradiction. So this indicates that we have, we made some assumption, and now this assumption here leads us to some sort of contradiction. Okay. So let's do this. So again, I'm going to try to prove the contrapositive. If L is not equal to M, then what happens? Well, I know that both of these statements are assumed to be true. So let's assume that this statement is true, this statement is true, and the opposite of this statement is true, and see if we arrive at any problems. So if L is not equal to M, then since the limit as x approaches a of f of x is equal to L, then, well, let's look up. What does that limit say? Oh, here, this is what the limit says. It says that for any epsilon, there's just a delta, so that this holds. Well, I'll give you guys an epsilon. This is my epsilon. And so I'm going to let epsilon, I can let epsilon, it has to be for every epsilon. So I'll pick one particular epsilon and see if I have any problems. So the epsilon that I'm going to choose here is 1/2 L minus M. Now, what are the only stipulations that I have on epsilon? One stipulation is that epsilon cannot depend on x. Well, it doesn't. It says that it's equal to L and M. And that it must be greater than 0. Well, I have an absolute value. And so I can't have an absolute value being less than 0. Well, could it be equal to 0? Well, sure, it could be equal to 0, but it could be equal to 0 only if I have that L is equal to M. If L is not equal to M, then this is greater than 0. Okay, good. So that's what I'm going to use here. I'm going to use, in the definition, my epsilon delta definition for limit, I'm going to let epsilon equal 1/2 times the absolute value of L minus M. So since the limit as, and maybe I'll write it here, what the limit says, just in case, even though we've said it 12 times. So what is the limit as x approaches a of f of x equaling L mean? Well, it means it's equivalent to, for every epsilon greater than 0, there exists the delta greater than 0, such that x minus a in absolute value being between any epsilon. So I can choose an epsilon. So what I'm going to do here is I'm going to choose an epsilon. And so the epsilon that I choose that was kind of big is, so 1/2 of absolute L minus M. So this is greater than 0. So I'm going to replace, and this is minus L, is less than epsilon. So that's my epsilon. So I'm just going to rewrite, my epsilon here as 1/2 times the absolute value of L minus M. You know, I could pick 12 or 50 or 17 for epsilon. I picked 1/2 absolute value of L minus M. It's a perfectly fine number. Now, I'm going to call this delta 1. Why? Just for the heck of it. Actually, it's because I have 2 of them. So I'm going to call this the first delta. So now, here's my statement. So now I can, actually, let me get rid of this. So here's my statement. If L is not equal to M, since the limit as x approaches a of f of x is equal to L, there exists a delta 1 greater than 0, such that x minus a in absolute value is between 0 and delta 1, implies that f of x minus L in absolute value is less than 1/2 times the absolute value of L minus M. It's exactly, there it is right there. So all I did is I just plugged into my definition of limit. Well, let's do the same thing. But now I'm going to, instead of saying, oh, let's make this. Yeah. Okay. Let's assume that this is M. There it is. Okay, so now let's make this equal to M. So everything's going to be the same, except I'll call this delta 2. Okay, so the only thing is instead of calling it delta 1, I called it delta 2. So there's a possibly different delta. So since the limit as x approaches a of f of x is equal to M, then there exists some delta 2 such that x minus a in absolute value being between 0 and delta 2 implies that f of x minus M in absolute value is less than 1/2 L minus M in absolute value. Wow, that statement there. Okay, good. So now, let me get rid of all that. Okay, so now, let delta be the minimum of delta 1 and delta 2. Well, since delta 1 is greater than 0 and delta 2 is greater than 0, then the minimum of those two numbers is greater than 0. If 12 is greater than 0 and 7 is greater than 0, then the minimum of 7 and 12 is also greater than 0. So delta is greater than 0. Then, well, if x minus a in absolute value is between 0 and delta, then absolute value of L minus M is equal to, well, let's note the following, that f of x, minus M minus f of x minus L is equal to, let me get rid of the parentheses, f of x minus M minus f of x minus and minus, make that a plus L. Notice that the f of x's cancel. So this is equal to L minus M. Oh, so if I take absolute values, certainly that's, since they're, what's inside the absolute value is equal, then certainly the absolute value of them are equal. And so I have that L minus M in absolute value is equal to this weird expression that I've written here. Okay, good. So L minus M in absolute value is equal to the absolute value of f of x minus M minus, in parentheses, f of x minus L. Now let's recall the triangle inequality. So if we recall the triangle inequality, we have that A plus B is less than or equal to absolute value of A plus absolute value of B. That is the triangle inequality. And we went, I told you yesterday when I first wrote this down, the triangle inequality, that it's going to be very important. And well, here's our first instance of using it. We're going to use it probably 50 times today, and probably 50 times tomorrow, and 50 times every other day. So we're going to use it a lot. So the triangle inequality. Absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. Okay, so now, notice I have here the absolute value of A plus negative f of x minus L, which is B, all in absolute value. So by the triangle inequality, this is less than or equal to the absolute value of this first guy, the f of x minus M, plus, well, the absolute value of the second guy. The absolute value of a negative, well, the absolute value just gets rid of a negative. And so it's the same as the absolute value of f of x minus L. But remember that delta is the minimum of delta 1 and delta 2. Therefore, if x minus a in absolute value is between 0 and delta, it's between 0 and delta 1. And so I have that this statement holds. And so I have that f of x minus L is less than 1/2 times the absolute value of L minus M. Similarly, oh, this is on the same page, so it's a little nicer. Similarly, since delta is the minimum of delta 2, then I have that x minus a in absolute value being between 0 and delta implies that x minus a in absolute value is between 0 and delta 2. Therefore, f of x minus M, that was L. I should have, the first one was L. This one is for M. Then f of x minus M is less than 1/2 L minus M in absolute value. And so I have this statement. And so I have that the absolute value of f of x minus m is less than 1/2 the absolute value of L minus M. And that's this statement. So I had this statement here, which came from this statement. And I have this other statement. Well, but now I notice I have 1/2 of some quantity plus another 1/2 of another quantity. So 1/2 of something plus 1/2 of the same thing is just the whole thing. So this is equal to L minus M in absolute value. But now I have that this number is less than itself. Can 12 be less than 12? Can 17 be less than 17? No, that's a contradiction. You can't have that a number is less than itself. And so we have a contradiction. And so it can't be that L is not equal to M. Therefore, we have proven what we wanted to show. Any questions about that? So this is really sort of the first time that you guys have seen proofs written out. Any questions about this?
Yeah, one question, Professor.
Sure.
Would you mind just quickly going over this again? I kind of got lost with the half.
Sure.
Just quick.
Oh, okay, so now the reason, so actually, I sort of, let's see if I can let me redo this. Actually, let's see if I can go, oh, wait. Let me do the following. I'm going to add a page. How the heck do I add a page? No.
I think it's at the top right. Under the red recording, it says plus.
Oh, thank you.
You're welcome.
I did it before, but I forgot. Thank you. Okay.
Yeah, no problem.
Okay, so I want to show the font. So I'm going to start out freehand. Okay. So I have that the limit as x approaches a of f of x equals L. And the limit as x approaches a of f of x equal m. I want to show that that implies that L is not equal to M. Okay, so let's try to prove this. So the first thing is that I'm going to make the assumption that L is equal to M. Okay. Oh. Of course, that's an incorrect statement, isn't it? Sorry about that. Okay, that's what we're trying to prove. I had an incorrect statement there. Sorry, that was a horrible typo there. My apologies. So let's assume L is equal to M. So that L is not equal to M. So let's assume that L is not equal to M. So what that means is that if I assume that L is not equal to M, then this must be greater than 0. Why is that a true statement? Well, the only way that an absolute value can equal 0 is if what's inside is 0. And I also have the absolute value is always greater than or equal to 0. So the only way that this could equal 0 is if what's inside was 0, but we're assuming it's not 0. Okay, so let me finish this now. So we have this statement here that the limit as x approaches a of f of x is equal to L. I will always start out these proofs sort of the same way. And so somehow I'm given an epsilon. Okay. Then I know that there is some delta greater than 0 such that x minus a in absolute value less than delta implies that f of x minus L in this case is less than epsilon. Okay, so I want somehow to have this involving the L and the M. So I'm going to actually just pick my epsilon. So I'm going to say, well, given, so rather than given epsilon, I'm going to say let epsilon equal L minus M. Now, I'll try that as my first guess. It turns out, and of course, this is going to be greater than 0, that at the end, I'm going to have to pick 1/2 of it. Why? Because I'm going to add them up. But I don't know that at this moment. So I'll just sort of try this as my first guess. And so what that means is that this here, oops, is the L minus M. Let's move this over a little bit. So I have some room here. So this is my L minus M. Okay, now let's do the same thing for this other one. Oh, why they both say M? Because I'm stupid. This one should say M. Okay, so that was, I had 2 typos in the statement. So now let's do the same thing. So the limit as x approaches a of f of x equals M. Well, I'll do the same thing, that epsilon equal L minus M, which is greater than 0. Then there is some delta. Since there's going to be 2 deltas, I'll make that delta 1 because there's another delta. So the only reason that I write these superscripts or subscripts is because I want to keep track of, these deltas. So then there exists some delta greater than 0 such that x minus a being in absolute value being between 0 and delta 2 implies that f of x minus M is less than L minus M. So now we're almost done. So now, and this is sort of the almost universal trick. Now that you have several deltas, you combine them into one delta by letting them be the minimum of delta 1 and delta 2. Well, since delta 1 is positive and delta 2 is positive, then both of these are positive. Okay. So now let's see what this implies. And so I have that L minus M, and it really doesn't matter. Let's do a minus M and minus L. That certainly is a true statement. And this is less than or equal to by the triangle inequality, each of these in absolute value. But now, if I look here, Oh, of course, I should say that since. So now this is all nice. This is a true statement, but I want to make some bound on this guy. And so to make some bound on this guy, if x minus a is less than delta, then since delta is the minimum of delta 1 and delta 2, then I have that x minus a in absolute value is less than delta 1. And it's also less than delta 2. Why have I stopped it? Here, wait 1 second. Connecting. Oh, okay, 1 second. I just lost my connection for a second. And now I'll get back. Sorry about that. Okay, start. Okay, I just lost my connection for a second. Okay, so now notice that since, let's do it for the L. Which one is L? Is delta 1. So delta 1 is L. Okay, so let's do delta 2 first. Oops, less than delta 2. Somehow that didn't write. Okay, less than delta 2. So now notice here, since x minus a in absolute value is between 0 and delta 2, then I have that this statement here holds. So I have that this is less than L minus M. Okay. And, well, this is also, oops. I forget how to undo it. So this is also here, x minus a in absolute value is also here less than delta 1. And so I have that this is, I'm sorry, that this, I already did that guy, that this here is less than that. So I can just add those up. Now, if you look here, well, that's all nice and fine, but I really want this to equal the L minus M. So if I put a halves in front of each of these, that will make it fine. So I'll just put a half in front of each of these. And if I do that, half plus a half equals a whole. And now that gives you your contradiction. So it was at the very end that I picked the half. So at the very end, I found out that, well, in order for these to add up to equal the whole, I needed a half of each. Of course, I didn't need to be a half. I could have picked 1/3 of this guy and 2/3 of the same thing, right, to make a whole. That would have worked also. So the fact that I just wanted them to add up to be the whole. So that's all I wanted, okay? It makes it easier to have them both equal to a half, but it wasn't necessary. Did this help or hurt? Did this explain the the problem, or did this hurt the
I
question?
think this helped me.
So at least
Yeah.
I have one. Any other questions about this? Okay.
So when we do a problem like this, at the end, we just put the railroad crossings to show that it didn't work.
Yes,
Oh, and the QED.
the railroad crossing means that it didn't work. The QED means I'm done.
Okay.
You could have more than one contradiction in a state, you know, in a proof. Usually you don't. But this just means there's this railroad crossing just means it's a contradiction. I've somehow found a contradiction. Okay, I've arrived at a contradiction. Any other questions? That seems sort of okay. No. Okay. If there are no questions, then I'm going to go on. I'm going to continue. So a left-sided limit, let f be a function defined on a left neighborhood of a, then the limit as x approaches a from the left of f of x equals L means that for every epsilon greater than 0, there exists a delta greater than 0, such that if x minus a is between minus delta and 0, then the absolute value of f of x minus L is less than epsilon. So I'm going to go up for a second to show you on my picture what I'm doing. So if I only look at this side, so a left-sided limit says that I can be sufficiently close to L. If I'm sufficiently close to L, then, so if I am close to L, then if I can find some distance to the left of A, so that I'm always, my y values are always in this epsilon tolerance of L, then this is a left-sided limit. So I'm only approaching A from the left. I'm only taking x values that are less than A. I'm still within my epsilon tolerance. Of course, for the right-sided limit, I'm going to be doing the same thing from the right. So, so let me do a right-sided limit. And so, and by the way, notice that this is just the interval on the left of A. Let's do a right-sided limit. Let f be a function defined on a right neighborhood of A. Then the limit as x approaches A of f of x from the right of f of x equals L means that for every epsilon greater than 0, there exists a delta greater than 0, such that x minus a being between 0 and delta implies that the absolute value of f of x minus L is less than epsilon. The following theorem says that in order for a two-sided limit to exist, we have to have that each one-sided limit must exist, the right-sided limit of A and the left-sided limit of A. And not only do they have to exist, but they have to equal the same value. And the two-sided limit is equal to that mutual value. So let me show you that in little pictures. So if, now let's do this. If I approach A from both sides, then the only way that that limit can exist from both sides, if the limit exists from the left side and the limit exists from the right side, and the left and right side limits are the same, then the two-sided limit exists and is equal to that mutual value. So let me restate that again. Aha. So theorem. The limit as x approaches a of f of x is equal to L, if and only if. The limit as x approaches a to the left of a of f of x is equal to L. And the limit as x approaches a from the right side of a of f of x is equal to L. And so we want to prove that. So notice that this is a if and only if. So that means I'm going to have to prove if this statement is true, then each of these statements are true. So I'm going to have to prove this. And I have to prove the other way, going this other way, that if these statements are true, then this statement must be true. So I also have to prove it going the other way. So this proof here will involve sort of two proofs, going from this assumption, proving these, so that's going to be this, starting with these, assuming that these are true, this way, and proving this at the end, which is proving this guy at the end. And so it will involve two proofs because it's an if and only if. So let's do this. So proof. So I'm going to do the proof here where I first assume that the limit as x approaches a of f of x is equal to L, and then I want to show that these are true. So here it is. I'm assuming this is true. So since the limit as x approaches a of f of x is equal to L, then, well, I'm just going to write down my epsilon delta definition. Then, given epsilon greater than 0, there exists a delta greater than 0. I'll call it delta 1, just like before, because I don't know why. Because I'm going to use a delta besides a delta 1. And so I'll call this delta 1. So given epsilon greater than 0, there exists a delta 1 greater than 0, such that x minus a in absolute value being between 0 and delta 1 implies that f of x minus L in absolute value is less than epsilon. So let delta equal delta 1 in the definition of the one-sided limit. So now I'm going to do my one-sided limit. So in the definition of the one-sided limit, let delta 1 equal my delta equal my delta 1. Certainly the delta 1 is greater than 0, so delta is greater than 0. And let epsilon be this given epsilon at the beginning. So I'm fixing my epsilon. It's the same epsilon that I have here in this thing. So if x minus a in absolute values between 0 and delta 1, well, then x minus a, by definition, if x minus a is between 0 and delta 1, then this is union to intervals. Then x minus, well, let's write it this way, I guess. Then minus delta 1 is less than, oops, x minus a. Is less than 0, and 0 is less than x minus a, which is less than delta 1, right? If you have a here, and this is a delta. This is delta. Then a open interval where you've taken out one point, a, which is what I've done here, is a union of these two open intervals. So certainly if x is in this whole interval, it's in, let's see, this is going to be the left one. So if x is in this whole interval, well, if x is in this left interval, then it's part of the whole interval. And so if x here is in the left interval, if x is between, if x minus a is between minus delta 1 and 0, maybe I should have written it this way, that it's, oops, a minus delta 1 in a, and this guy over here is a less than x less than a plus delta 1. So here's my left interval, and here's my right interval. So and we're doing first this guy. So here's my left interval. So if x is in the left interval, it's certainly in the whole interval here. But if x is in the whole interval, then f of x minus L in absolute value is less than epsilon. So therefore, f of x minus L in absolute value is less than epsilon. But this means, if you look here, this is just the definition of the left-sided limit. Therefore, the left-sided limit exists and is equal to L. Similarly, let's do it on the other side. So similarly, let delta equal delta 1, which is certainly greater than 0, as before. So if x is on the right side of your of A, then it's in this two-sided interval. And from above, we have the f of x minus L in absolute value is less than epsilon. So therefore, just like before, if x minus a is between 0 and delta 1, then f of x minus L in absolute value is less than epsilon. So again, that means that the right-sided limit exists and is equal to L. So the limit as x approaches a from the right of f of x is equal to L. And so I've shown that the left and right-sided limit exist and they're both equal to L. And that's what I wanted to show. Okay, good. Let me get rid of that. So now let's do it the other way. So now I want to go in the other direction. So I'm going to assume that both the right and left-sided limits exist. Show that that implies that the two-sided limit exists. And so I'm going to have that, well, say this is A. And I'll get some delta 1. And that will map into, I made it kind of big. This will map into my, say this is L and this is epsilon. Oops. Okay, so somehow I have a delta 1 and my F's map all my X's here in a delta tolerance of L. That's because the left-sided limit exists. So since the limit as X approaches A of f of X is equal to L, for X's being less than A, then we have given epsilon greater than 0, there exists a delta greater than 0 such that if X is to the left of A, so if X minus A is between negative delta 1 and 0, then the absolute value of f of X minus L in absolute value is less than epsilon. So if we're here to the left side, then we'll be in this epsilon tolerance of L. Well, we also have that, and that's because the left-sided limit exists. Suppose the right-sided limit also exists. Well, if the right-sided limit also exists, then there exists a delta 2. Not necessarily the same size as that delta 1. There's another delta, and so I'll call it delta 2, that maps, so F again, maps all those into the epsilon tolerance of L. So there's some, so since f of X, well, since the limit is X approach A from the right, f of X equaling L, then there exists a delta 2 greater than 0. And this is given this epsilon. I'm fixing my epsilon. So fixing my same epsilon, there exists a delta 2 greater than 0 such that if X is on the right side of A, so X minus A is between 0 and delta 2, then f of X minus L in absolute value is less than epsilon. Okay, so now, if I take the smaller of the two, so now if I take the smaller of the two, so let delta be the smaller of the two, so let this delta here be the smaller of these two guys, then that means that this interval is going to be within the bigger one. And so all of the x's map to the epsilon tolerance. Okay. So let delta be the minimum of delta 1 and delta 2. Certainly that's greater than 0 because both delta 1 and delta 2 are greater than 0. Then if x minus a in absolute value is between 0 and delta, meaning I'm in here, then f of x minus L in absolute value is less than epsilon. Sure, because everything in this interval mapped, whatever. Everything in this interval here mapped here, and everything in this interval mapped here. Therefore, everything in this smaller interval, the thing that's inside the bigger interval, has to map into here. So I can get rid of this. And so I have that if x minus a is between 0 and delta, then f of x minus L in absolute value is less than epsilon. And that's just the epsilon delta definition of a limit, the two-side limit. So therefore, the limit as x approaches a if f of x exists and is equal to L. And that's what I wanted to show. I've shown it both ways, so I'm done with the complete proof. Any questions about this? So I had to prove it both, going in both directions. Any questions?
I have a question. On an exam or something, are we gonna have to do a proof, or if we could just figure out how to? Okay.
Yes, so you will have to figure out, well, let me just say, you will need to mimic these proofs. So in other words, I've gone over these proofs. All you'll need to do is just to reiterate what I did. So it's not like you have to be super inventive, because I've already done it. And so you'll just have to sort of reiterate some these type proofs. Now, there may be some in the future, you'll see some other proofs that involve equations. And those will be, different for differing people that on exams. But things like this, these are fixed. So you may have on an exam a question that says, prove this, okay? And I would expect that you give something similar to this, okay? So you don't need to be inventive, because it's already here. You've already seen it. What you'll notice is that at the beginning, all of these proofs look different, unique, and like I've done something magical. Hopefully by tomorrow or the next day, you'll see that all of them are all the same. They all start out the same, they all proceed the same. And it's really that I'm just doing the same thing over and over and over again. It's like when you solve an equation, the fact that you added 2 to both sides, or in the next equation you add 3 to both sides, that's really, you're doing the same thing. It's the same thing here. I'm always doing the same thing. It's, of course, you have, right now you've only seen 2 examples. By the time you see 50 examples, you'll be sick and tired of me doing the same thing over and over again. Okay, hopefully that answered your question.
Yeah, thank you.
Okay. I don't know if you like the answer, but hopefully that answered your question. Let me do the next problem. Okay, so theorem. If the limit as x approaches a of f of x is equal to L, and if L is greater than 0, then there exists a delta greater than 0, such that f of x is greater than 0 for every x in the union of the open intervals, a minus delta to a, union the open interval, a to a plus delta. So what the heck am I talking about? So this is actually something very intuitive. So suppose that I have a here, and suppose that I have some function. No, I'll just have it open here. So this is y equal f of x. Suppose that I have that the limit exists for this function and it's greater than 0. Then that says that, well, somewhere my function has to be in some interval always bigger than. So here, all my y values are greater than 0. So somehow, if the limit is greater than 0, then near L, I've got to be greater than 0. So it's saying that, well, oops. As x approaches A, my y values approach L. If L is greater than 0, then somehow when I'm very close to A, all my y values must be greater than 0. Since the y values were close to L and L was greater than 0. So somehow, if I get sufficiently close, all my y values will be positive. And that's all it's saying. Okay. So, oops. So let's try. So that's what this is saying here, that in the deleted neighborhood, that there is some delta deleted neighborhood of A, so that all my y values are greater than 0, since for every epsilon greater than 0, f of x, that if there exists some deleted neighborhood of A, so that f of x minus L is always less than epsilon. So that means you're sufficiently close to L, but L was positive. And so you're sufficiently close to a positive number. If you make it sufficiently close, I can be sufficiently close. So I'm always, so let's say that this is L. And this is my x-axis. So I want to be sufficiently close to L. So I want to be such that if I take epsilon here, that I'm always guaranteed that this interval will be above the x-axis. Well, I can do that by guaranteeing that this epsilon here is less than L. Well, how do I make it less than L? I don't know. I'll arbitrarily make it half of L. That's certainly less than L. It was arbitrary. I could have picked, 0.9 L or something. It really didn't matter. I picked a half because half is a nice number. So there's nothing magical about a half. It's just that I wanted epsilon here to be less than L. And so I, 1/2 of L is going to be less than L. Okay, so since L is greater than 0, then given epsilon, and I'll pick my epsilon to be what I just told you a second ago, L divided by 2. Well, since L is greater than 0, then L divided by 2 is greater than 0. So my epsilon is greater than 0. Since the limit as x approaches A of f of x is equal to L, then there exists some delta greater than 0, such that x minus A in absolute value between 0 and delta implies that f of x minus L in absolute value is less than L over 2. Epsilon is less than epsilon. And I pick epsilon to be L over 2. Okay, so now, well, I have an absolute value inequality. Let me rewrite that absolute value inequality as a 3-part inequality. And so the absolute value of x being less than A is the same as x being between A and negative A. We went over that yesterday. And so the absolute value of f of x minus L being less than L over 2 is the same as f of x minus L being between minus L over 2 and plus L over 2. Let's add L to all sides of my inequalities. So L minus L over 2 is L over 2 is less than. The L's cancel, so I get f of x. L plus L over 2 is 3L over 2. And so I can just look at this side. So it says f of x is greater than L over 2. But, well, L over 2, L is positive. So L divided by 2 is greater than 0. And so f of x is greater than 0. And so I've proven what I wanted to show, that if x minus a in absolute value is between 0 and delta, then f of x is greater than 0. And so I'm done. Any questions about that? Let me do the following theorems. Limit as x approaches a of c is equal to c. So the limit of a constant is that constant. The limit as x approaches a of x is equal to a. So certainly this is, these are obvious statements. As x approaches a, let's say that c is 12. So what does 12 approach as x approaches 3? Well, 12 is always equal to 12. So 12 approaches 12 as x approaches 3, or as x approaches 25, or as x approaches 77. So if y is always a constant, then it doesn't matter what the limit is because it's just a constant. So if you have here, say this is y equals c, and let's say that this is a. Well, as x approaches a, my y values are always just going to be c, so therefore the limit is c. Similarly, say this is y equal x. So this is a here. As x approaches a, well, my y values, remember that these are the same, y equal x. So whatever this number here approaches the same number. So this approaches a. And so as my x approach a, my y values also approach a. And so the limit as x approaches a of x is just equal to a. Oops. There it is. Okay, so let's do this. Now, so again, how do you start the proof? So I'm going to prove the first one. I'm going to prove this guy here. So how do I start the proof of a limit? Well, we start always the same way. We just write the definition of this statement here. So given epsilon greater than 0, there exists a delta greater than 0, such that if x minus a in absolute value is less than delta, then the absolute value of f of x minus L is less than epsilon. F of x is always equal to c. I'm letting L be c. So c minus c in absolute value is 0. And so I can pick epsilon to be anything greater than 0. I pick it to be delta. just because, I mean, who cares? It could be anything. I could let, epsilon be any sort of, or let delta be anything involving, I could let delta always equal 1, and this would still be a true statement. So I could have said, instead of let delta equal epsilon in this case, I could have said let delta equal 1, and then this would have been a true statement. Well, so given epsilon greater than 0, that delta equal epsilon, which is greater than 0, then if x minus a in absolute value is between 0 and delta, then the absolute value of c minus c is 0, which is less than epsilon. Therefore, this implies that, maybe I should have said that. This statement here implies that the limit as x approaches a of c is equal to c. And that's what I wanted to prove. So I'm done. Now let's try to do the next part. Well, it's going to be the same type, of proof. And so, given epsilon greater than 0, let delta equal epsilon, which is greater than 0. Then x minus a in absolute value being less than delta implies that x minus a in absolute values between 0 and epsilon, because I'm letting delta equal epsilon. But then just looking at this, says that x minus a in absolute value is less than delta. Is less than epsilon. And so this says that, so let's retranslate this statement here. So let's retranslate this. And so I have the limit, this is the limit as x approaches a of f of x, which in this case is x, is equal to L, which in this case is A. And that's what you wanted to prove. So I'm done. Any questions about that? Okay, let's go on to the next one. Okay, so actually maybe what I'll do is I'll prove it above in this little bitty space, and then I'll go over the proof. Okay, so if M, B, A are real numbers, then the limit as x approaches A of mx plus b is equal to ma plus b. So let's try to prove this. So I'm going to try to prove this, and I'm going to put it here. Oops. So I'm just going to put it in this little space here. So my proof, oops, stop. My proof will be the following. So I want to show this statement here. And I'm just going to, so the first step is, well, just write it, the definition, the epsilon delta definition. So I'm not even going to think. I'm just going to say, well, so limit, oops, limit as x approaches a of mx plus b of mx plus b equaling ma plus b. Well, this, by definition, says given epsilon greater than 0, there is a delta. So let delta equal, I don't know what I should let delta equal. I'm going to leave that blank. But I know that delta has to be greater than 0, such that, well, if x minus a is less than delta, whoever that delta is, then f of x minus L is less than epsilon. So at the end, I want epsilon. And now I got to figure out what I need in between to make it a true statement. So let's fill in what's in between. Well, first off, I'll get rid of the, so first thing to do is just try to simplify this. So let's try to simplify this absolute value expression. And so I have here, well, let's get rid of the parentheses. And so I have mx plus b. Let me change, since I have a negative sign outside the parentheses, let me change all the signs inside the parentheses. So I have a ma minus b. But now the b's cancel. So this is equal to m x minus ma. And so now if I look at this, well, somehow I want it to involve this guy. If I have something involving this guy, then I'll be able to bound this guy. And so let's factor out an m. And I'm going to do this in absolute values. Recall that the absolute value of AB is the absolute value of A times the absolute value of B. And so this is just the absolute value of M times the absolute value of X minus A. Okay. Now I want this to be equal epsilon. So this is my delta. I want to make delta so that when I multiply by m, I get something less than epsilon. So what I could do is, well, let's divide by m. So I could say, well, let this be, yeah, whatever. I could say, let this be there. M, and then maybe epsilon over m. Then the m's would cancel, right? And I get that this is epsilon. Now, of course, I can't have that these are equal, but this is a less than. So that's a less than this. Okay, everything's fine except for one problem. What's the one problem that, so this proof is okay except for one error. What is my error? What if m is 0? If m is 0, then I'm dividing by 0. And so I don't want to divide by 0. And so because of that, I don't want epsilon over m, because if I do that, then I'm dividing by 0. But I do want, so I want something that's less than, less than this. Okay. So I can do that by making it bigger, by making the denominator bigger. And so I can let the denominator be m plus 1. Okay, so let's change this to be the following. So now what I'm going to do is let this be epsilon over m plus 1. Okay, and then this is going to be less than epsilon. So I should let delta equal epsilon over m plus 1. Now, let me do the following. So I'm going to, that's all nice and fine if and maybe I'll show this. If I have that, well, maybe I'll do as an X or something, or a B, or I don't know. I want to show that that's always less than 1 if B is greater than 0. Okay, well, that's certainly a true statement because, well, certainly 0 is less than 1. That's certainly a true statement. I can add B to both sides of this. And so if I add B to both sides, I get that B is less than B plus 1. Now, B is greater than 0. So B plus 1 is greater than 0. So I can divide both sides of my equation by B plus 1. So B over B plus 1 is less than 1. And that's what I wanted to show. So this guy here, the absolute value of M over the absolute value of M plus 1, I know that's less than 1. So therefore, this quantity here is less than epsilon. So now I'm done. So that says that the limit exists and is equal to what I want. So let me actually do this for real. So that was just sort of an aside proof. Okay, so let's prove the theorem. If M, B, and A are real numbers, then the limit as x approaches the limit as x approaches A of mx plus b is equal to ma plus b. So given epsilon greater than 0, let delta equal epsilon over absolute value of m plus 1, which is greater than 0. Since an absolute value of m plus 1 is always greater than 0, and epsilon is greater than 0, then their ratio is always greater than 0. So then, if the absolute value of x minus a is between 0 and delta, this is the same as saying that the absolute value of x minus a is between 0 and epsilon over absolute value of m plus 1. Then let's look at this inequality. Let's look at this difference, the absolute value of this difference. The absolute value of the quantity mx plus b minus the quantity ma plus b, that's equal to, well, again, distributing the minus sign inside the parentheses. I have that this is equal to mx plus b minus ma minus b. The b's cancel. So I just get the absolute value of mx minus ma. Let me factor out an m. So by the properties of absolute value, this is just equal to the absolute value of m times the absolute value of x minus a. But remember, the absolute value of x minus a is less than epsilon over absolute value of m plus 1. But the absolute value of m divided by the absolute value of m plus 1 is less than 1. And so the absolute value of m times epsilon divided by the absolute value of m plus 1 is less than epsilon. But now this says that the limit as x approaches a of mx plus b is just ma plus b. And that's what you wanted to show. Any questions about that? You could have also done this where you split it into two cases. One where m is not 0 and the other case where m is equal to 0. And you could have done it separately. So one technique of proof is to find this delta where it's true for all cases. another way of doing this is to do it where, well, it really doesn't matter, where we do two cases, where m is 0 and where m is not 0. And you separate them out, getting two differing, two differing deltas for your epsilons. Okay. Theorem. Let's prove the next theorem. The fact that, three of these, actually it's, four of these, that four statements are equivalent. So I'm going to write down four different statements involving limits, and I want to show that these four statements are equivalent. So the limit as x approaches a of f of x equaling L is the same as the statement. The limit as h approaches 0, f of a plus h equaling L, which is the same as the statement. The limit as x approaches a of f of x minus L equaling 0, which is the same as the statement. The limit as x approaching a of the absolute value of f of x minus L equaling 0. So there are, well, maybe I should write them. There are 1, 2, 3, 4 statements here. So there are 4 statements here. If I can show, assuming 1 implies 2, and 2 implies 3, and 3 implies statement 4, and then 4 implies statement 1, then that means that they're all the same. So if I can go in this loop here, just like what I did before, where I showed that well, I guess I didn't have, I did have 2 statements. Well, so I did have one where I had 2 statements, where 1 implied 2, and then I did that 2 implied back 1. So I loop back on itself. Therefore, they're always, say you want to show that statement 2 is equivalent to statement 4. Well, 2 goes to 3 and 3 goes to 4, therefore 2 goes to 4, etc. So if you pick any of the statements, you can somehow loop back to them if I'm able to show this. Okay, so let's do this. So I'm going to do, first, that statement 1 implies 2, 2 implies 3, 3 implies 4, and then lastly, that 4 implies 1. And that gives me my big loop back, so I show that therefore all of them are the same. Okay, so let's do this. So statement 1, I want to show that if I assume that this statement is true, then I can show that this statement is true. So how do you prove something like this? Well, what you do is the following. You start at the beginning, you end at the end, and then you fill out what's in between. So you start out, say I wanted to show that this implies this. So I would say, so this is 1 implies 2. So I would say, well, limit as x approaches a of f of x equals L. Then do a whole bunch of stuff, and then at the end, that implies that the limit as x approaches 8 is, I'm sorry, the limit as h approaches 0 of f of a plus h equals L. Okay, so now rewrite this in terms of epsilons and deltas. And so you would say, well, given epsilon greater than 0, there exists a delta greater than 0, such that x minus a in absolute value being between 0 and delta, that implies that f of x minus L is less than 0, is less than epsilon. Okay. Let's rewrite this last statement here in terms of epsilon and deltas. So somehow I want to show this. Now, of course, it may not be the same delta. So maybe I'll put a delta 1 here or something. Okay. So given epsilon greater than 0, we'll have the same epsilon. So given the same epsilon, there exists a delta greater than 0, such that if x minus a in absolute value is less than delta, then, oh, I need more room here. Then absolute value of f of a plus h minus L is less than epsilon. Okay, so that's basically what I want to do here. Now, if I look here, oops. Oh, this is h minus 0. I have an error. I have an error here. I have an error. This is h minus 0. Okay. So if I look here, well, this is just h. And this is an x minus a. Actually, these deltas may even be the same deltas. So it's possible, actually, that these deltas are the same. So if I look here, I have here an absolute value of x minus a. And I have here the absolute value of h. So maybe if I somehow rewrite, this, where I've replaced x by, or x minus a by h, or at least thought of it as being the same, okay? Or thought of x as being a plus h, just adding a to both sides of my equation. So let's think of, let's sort of think of this, oops. Let's think of x as being a plus h. Oh, okay, so instead of writing x, I'll just write a plus h. And so if I do that, this is the same as, oops, 0 less than, or maybe I should write so. So let's write x as a plus h. That implies write x as a plus h. Well, notice that the a's cancel. If f of x is equal to L, then given epsilon greater than 0, there exists a delta 1 greater than 0, such that x minus a in absolute value being between 0 and delta 1 implies that f of x minus L in absolute value is less than epsilon. Then let delta equal delta 1 greater than 0. then absolute value of h is greater than 0, and it's less than delta 1. And that's equal to, well, the absolute value of h, actually h, is equal to a plus h minus a. The a's cancel. And so if a plus h minus a in absolute value is between 0 and delta 1, then by the above, we have that the absolute value of f of x plus of f of a plus h minus L is less than epsilon. But that means that the limit as h approaches 0 of f of a plus h is L. And so we're done. Any questions about this proof? Okay. Now let's do that 2 implies 3. So I want to show this. That the limit as h approaches 0 of f of a plus h equaling L implies that the limit as h approaches 0 of f of x minus L is equal to 0. So let's show that. Since the limit as h approaches 0 of f of a plus h is equal to L, then given epsilon greater than 0, there exists the delta 1 greater than 0, such that if the absolute value of h minus 0 is between 0 and delta 1, then the absolute value of f of a plus h minus L is less than epsilon. Let delta equal delta 1, which is greater than 0. Then the absolute value of x minus a, well, then x minus a in absolute value being between 0 and delta 1 implies that, well, the absolute value of x minus a minus 0 is between 0 and delta 1. Subtracting 0 doesn't change anything. And so just subtracting 0 from x minus a doesn't change anything at all. But then I have something minus 0 in absolute values between 0 and delta 1, which is this statement. That implies that the absolute value of f of a plus that something minus L is less than epsilon. And so that implies that the absolute value of f of a plus x minus a minus L is less than epsilon. But this, the a's cancel. So this implies that f of x minus L in absolute value is less than epsilon. But again, subtracting 0 or adding 0 to anything doesn't change that object. And so I have that this implies that that f of x minus L minus the quantity f of x minus L minus 0 in absolute value is less than epsilon. But this just says that the limit as x approaches a of f of x minus L is 0. And so I've shown that statement 2 implies statement 3. Any questions about that? Okay. Let's show that statement 3 implies statement 4. Oops. Here it is. That statement 3 here implies statement 4. So basically, you just put an absolute value here. So the limit as x approaches a of f of x minus L equaling 0 implies that the limit as x approaches a of the absolute value of f of x minus L is also equal to 0. So let's prove that 3 implies 4. Here it is. So let's show this. Well, my assumption is that the limit as x approaches a of f of x minus L is 0. So since the limit as x approaches a of f of x minus L is 0, then given epsilon greater than 0, there exists a delta, let's call it delta 1 greater than 0, such that x minus a in absolute value is between 0 and delta 1, implies that the absolute value, well, implies that the quantity f of x minus L minus 0 in absolute value is less than epsilon. Well, let delta equal delta 1, then if x minus a in absolute value is between 0 and delta 1, this thing, same statement here, then the absolute value of f of x minus L minus 0 is equal to, well, look, I'm subtracting 0. So I'm not doing anything. So I'm taking the absolute value of f of x minus L, subtracting 0. So that's just the absolute value f of x minus L. I'm taking the absolute value of that, which doesn't give me anything different because it's already non-negative because I've taken absolute value. So this is equal to the absolute value of f of x minus L. Again, I can subtract 0. That's not going to change anything. So this is equal to the quantity f of x minus L minus 0 in absolute value. But if x is in this interval, which it is, then we have that this inequality holds. And so this is less than epsilon. And so I've shown that this quantity here is less than epsilon. Therefore, I've shown that the limit as x approaches a of the absolute value of f of x minus L is 0. And that shows that the third statement implies the fourth statement. Any questions about that? You notice that eventually all these look the same, that they all sort of follow the same logic. Lastly, let's prove that statement 4 implies statement 1. That the limit as x approaches a of the absolute value of f of x minus L equaling 0 implies that the limit as x approaches a of f of x is equal to L. So let's do this. Since the limit as x approaches a of the absolute value of f of x minus L is 0, then given epsilon greater than 0, there exists a delta 1 greater than 0, such that if x minus a in absolute value is between 0 and delta 1, then the absolute value of f of x minus L minus 0 in absolute value is less than epsilon. Let delta equal delta 1, and of course that's greater than 0. Then if, or I should have said with the delta first, if x minus a in absolute value is between 0 and delta, then x minus a in absolute value is between 0 and delta 1. And so the absolute value of f of x minus L is equal to, well, if I subtract 0 from this, I'm not going to change its value. Or if I take the absolute value yet again of this, it's not going to change its value. So this is equal to the absolute value of f of x minus L minus 0, and then you take its absolute value yet again. But this, since this is true here, then I have that this is true. So this is less than epsilon. Therefore, this is less than epsilon. And so the limit as x approaches a if f of x is equal to L. And that's what you wanted to prove. So you're done. And so I've gone the whole route. I've gone the whole circuit, and I've shown this. Any questions on, this is a longer proof. Any questions on this? The fact that these 4 statements here are true. Any questions on that? Okay, so I can even just put it here. Let L here equals 0. So let L equal 0 here. I know that statements 3 and 4 are the same. And so if I do that, then L equals 0, then these statements are the same. So I have that the limit as x approaches a of f of x minus L equaling 0 is equivalent to the limit as x approaches a of the absolute value of f of x minus L equaling 0. And so if I let L equal 0 in the above theorems, then I see that these 2 statements are equivalent. Okay, good. That all seems nice and fine. Now let me just do another one. And so notice that this is going to now be a little bit more subtle. The limit as x approaches a of f of x is equal to L implies that the limit as x approaches a of the absolute value of f of x is equal to the absolute value of L. But it turns out that if you try to assume that this is true, this statement actually is not true. It's not implied. And so I can only really go one direction. So first, let's prove. If I assume that the limit as x approaches a of f of x is equal to L, let me show that the limit as x approaches a, the absolute value of f of x is equal to absolute value of L. Well, start out like always. Since the limit as x approaches a of f of x is equal to L, then given epsilon greater than 0, there exists a delta greater than 0 such that x minus a in absolute value being between 0 and delta implies that f of x minus L in absolute value is less than epsilon. So if x minus a in absolute value is between 0 and delta, then let's look at this guy, which is what we want to prove. We want to prove this statement. The absolute value of f of x minus the absolute value of L. If I take the absolute value of that, that's equal to, well, the absolute value of A minus the absolute value of B is equal to the absolute value of A minus B. So let's show that this is a true statement. Well, the absolute value of A minus absolute value of B. And so either A and B are going to have the same sign. Well, this is less than or equal to, by the way. So either A and B are going to have the same sign. So if A and B have the same sign, then let's say that both A and B are greater than 0. Okay. And so if A and B are greater than 0, then certainly this is the same as A minus B. Let's say that A and B are both less than 0. Then the absolute value of A will equal negative A. Absolute value of B will equal negative B. So then these are just equal to the negative of each other. And so if I take the absolute value of everything, then there's the same. Okay. So if the signs are the same, then this is going to be equality. Now let's suppose that one is greater than 0 and the other is less than 0. Then the absolute value of A minus absolute value of B. Well, the absolute value of A is just A. Absolute value of B is minus A, is minus B. Okay. But now this is going to be less than A minus B. Well, maybe I should say it this way. This is going to be, this is a, some positive number. Okay. And so, right. So this is some number, but this is going to be, well, this is going to be the same thing. Okay. Now suppose I have A is less than 0 and B is greater than 0. This will equal a minus A minus B, which is, well, the same as the absolute value of A plus B, which is less than your A minus B. So no matter what, depending on your signs that you have, this, oops. This is the inverse triangle inequality. So this statement here, the inverse triangle inequality, says that the absolute value of A minus the absolute value of B in absolute value is always less than or equal to A minus B. And so by in this statement here, the inverse or the reverse triangle inequality, I have that this is true. Therefore, I have that the absolute value of the absolute value of f of x minus the absolute value of L is less than or equal to the absolute value of f of x minus L. But the absolute value of f of x minus L is less than epsilon, so long as x minus a in absolute value is between 0 and delta, which it is. And so this is less than epsilon. Therefore, I've shown that this is less than epsilon. So the limit as x approaches a of the absolute value of f of x is equal to the absolute value of L. And that's what you want to know. So we have here that the limit as x approaches a of the absolute value of f of x is equal to the absolute value of L. And that's what you wanted to show. Any questions about that? I'm not sure if I gave the correct intuition for the reverse triangle inequality, but that's certainly a true statement. Any questions about anything? Okay, so let's show that you can't switch this around. That if this is true, I don't get that this is true. So let's do an example. So let's show a counterexample. Let f of x be defined as follows. Let it equal 1 if x is a rational number. Let it equal -1 if x is an irrational number. Well, let's take the absolute value of f of x. The absolute value, well, it's either equal to 1 or -1, but the absolute value of 1 and -1 is the same. It's always equal to 1. So the absolute value is just always equal to 1 for all x, for all real numbers x. Therefore, the limit as x approaches 0 of the absolute value of f of x is just equal to 1, because you're taking the limit of something that's always equal to 1. But let's look at the limit as x approaches 0 of f of x. Well, as x approaches 0, let's take numbers that are rational. If you take a number near 0, well, if it's rational, then f of it is going to be equal to 1. But if it's, take another, remember in between any two rational number is an irrational number. So I can take a irrational number that's even closer to 0, and I get a -1. Take in between a irrational number and a rational number is also another rational number. So take a number that's even closer, and you'll get a 1. So it keeps oscillating. As you keep getting closer and closer to 0, it keeps oscillating between plus or minus 1, depending on if you are at a rational number or if you're at an irrational number. And so this limit does not exist. So the limit as x approaches 0 of f of x does not exist. As a matter of fact, neither of the one-sided limits exist either. And so neither, the right-sided limit or the left-sided limit exist. Certainly, the two-sided limit also does not exist. So therefore, the limit as x approaches 0 of f of x is not equal to, plus or minus 1. And so the converse of the theorem does not hold. Any questions about that? So that gives you a counterexample to this particular theorem that we just showed. So it means that we can't do better than that statement where I'm proving it one way. Of course, you can maybe have some additional assumptions to make where it will go the other direction. Okay, so now let's do the following theorem. This is a very long theorem. So I think this is the theorem. Okay, so this is the theorem. It's basically, this theorem here is all of the properties for limits. And once we have all these properties of limits proven, we can then actually go and calculate limits easily, because these properties of limits will easily show us how to compute limits. And we'll go back in section 1.6, use these use these properties of limits to calculate easily limits. Okay, so theorem. Let L, M, and A be real numbers. Assume the following. The limit as x approaches A of f of x is equal to L. the limit as x approaches a of g of x is equal to m. Please note, just recall that when we write a statement of this type, this means that the two-sided limit exists and that it's equal to this number L. And so that the two-sided limit must exist and that the value of the two-sided limit is L. Also assume that the limit as x approaches a of g of x is equal to m. The reason for these assumptions here, this notation, is that it makes it easier to actually do the proofs if I have some numbers to deal with. It's then I can plug those into my epsilon delta definition. So I want to write them in this fashion to make the proofs easier. So first, well, let me just quickly say what they are and then I'll read them. So the limit of a sum is the sum of the limits. The limit of a product is the product of the limits. The limit of a quotient, well, the limit of a reciprocal is the reciprocal of the limits, so long as you're not dividing by 0. The limit of a quotient is the quotient of the limits, again, so long as you're not dividing by 0. The limit of a scalar multiple is the scalar multiple of the limits. The limit of a difference is the difference of the limits. So let me read these off. If the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of g of x is equal to m, then 1, the limit as x approaches a of f of x plus g of x is equal to L plus m. 2, the limit as x approaches a of f of x times g of x is equal to L times m. 3, if m is not equal to 0, then the limit as x approaches a of 1 over g of x is equal to 1 over m. 4, if m is not equal to 0, then the limit as x approaches a of f of x over g of x is equal to L over m. 5, the limit as x approaches a of c times f of x is equal to CL. And 6, the limit as x approaches a of f of x minus g of x is equal to L minus m. Now, it turns out that we could actually use this. Well, let me say this. I can use this to prove this. I could then use this guy and this to prove this. And I could prove this and then use this guy to prove this guy. And so I really only would need to show half of these, 3 of these. Actually, I would really only need to, well, no, these first 3. I would need to show these first 3. From those, the last 3 hold. But I'm not going to do that. I'm actually going to assume that I don't know anything and prove these directly. Why? Because it helps you. Because it shows you how to prove them from the beginning, rather than as a consequence of things that you've shown before. And so I'm just going to prove each of these as if I didn't know anything from before. Okay, so let's try to show this. First one. Oh, and notice that these are all separate from each. So I'm going to assume that each of these are separate from each other. So even though this is one big theorem with 6 parts to it, this is really 6 differing theorems, all written as one gigantic theorem. So think of this as just one gigantic, one, rather than one, rather than saying it's one gigantic theorem, this one gigantic theorem is really 6 separate theorems. And so I'm going to be proving these 6 separate theorems. So I want to show that the limit of a sum is the sum of the limits. Since the limit as x approaches a of f of x is equal to L, and this is why we use this notation, because now I can do the epsilon delta. I can use the epsilon delta definition. Since the limit as x approaches a of f of x is equal to L, then given epsilon greater than 0, there exists a delta 1 greater than 0, such that if x minus a in absolute value is between 0 and delta 1, then f of x minus L in absolute value is less than 1/2 epsilon. So my epsilon that I'm going to be using is really 1/2 epsilon. So I'm going to be using in this definition, rather than epsilon, I'm going to be using 1/2 epsilon. And that gives me a delta, which I'll call delta 1. Next, I'll do the same thing. So I'm going to do the same thing, but I'm going to do it given the same epsilon. So given this epsilon here is fixed, so I'm going to fix this epsilon. And I'm going to now do the same thing, but now for this. So since the limit as x approaches a of g of x is equal to m, then, given my epsilon, which I'm going to write here as epsilon, 1/2 epsilon. So given my 1/2 epsilon greater than 0, there exists a delta, I'll call it delta 2, such that if x minus a in absolute value is between 0 and delta 2, then g of x minus m in absolute value is less than 1/2 epsilon. So now, let delta equal the minimum of delta 1 and delta 2, just like what we've done before. Certainly that's going to be greater than 0, because each of these are greater than 0. Then, if x minus a in absolute value is between 0 and delta, then the absolute value of f of x minus, f of x plus g of x minus, in parentheses, L plus W, L plus M. And that's equal to, well, let me get rid of the parentheses. And so the absolute value of, well, f of x plus g minus, let's distribute the minus inside the parentheses. So minus L minus a plus W, so that's a minus, why I say W? Second time I've said W. Minus plus M gives you a minus M. And now let's group these together. So I have a f of x minus L and a g of x minus M. Now I can now use the triangle inequality to take, so the sum, the absolute value of a sum is less than or equal to the sum of the absolute values. And that's your triangle inequality. And so the absolute value of f of x minus L plus g of x minus M is less than or equal to, by the triangle inequality, the absolute value of f of x minus L plus the absolute value of g of x minus M. But since x minus a in absolute value is less than delta, and delta is the minimum of delta 1 and delta 2, then f of x minus a in absolute value is between 0 and delta 1. Therefore, f of x minus L in absolute value is less than 1/2 epsilon. Similarly, since delta is the minimum of delta 1 and delta 2, and since x minus a in absolute value is between 0 and delta, then x minus a in absolute value is between 0 and delta 2. Therefore, the absolute value g of x minus m is less than epsilon over 2. So therefore, the absolute value of f of x plus L plus the absolute value of g of x minus m is less than 1/2 epsilon plus 1/2 epsilon. But, well, a 1/2 epsilon plus 1/2 epsilon is just epsilon. But now, if you look here, this says that the limit as x approaches a of f of x plus g of x is just L plus m. So I've shown that the limit as x approaches a of f of x plus g of x is equal to L plus m, and that's what I wanted to show. Next. What else do I want to, what's 2? Oh, the product. 2 is the product. Sorry. So 2 is the product. And so for property 2, I want to prove that the limit of a product is the product of the limits. We'll start the same as before. And so maybe let me give you a little, let's see what happens. So let me give you a hint at what happens. So I have here, I want to show that the limit as x approaches a of f of x times g of x is equal to L times m, where the limit, so maybe I should say where, or maybe, I'll write it this way. So the limit as x approaches a of f of x equals L limit as x approaches a of g of x equaling m implies this statement here. Oops. I don't remember how to do the inverse. Okay. Implies limit as x approaches a of f of x, g of x is Lm. So the first thing I want to do is just write out what this statement means, what this statement means, and then let's write this statement at the very end that I want to obtain. So let's write the statement first. So I have here, given epsilon greater than 0, there exists a delta. Well, maybe I'll just say let delta. Let delta equals something greater than 0. Then x minus a in absolute value between 0 and delta 1, let's call it delta 1, implies that, well, this is f of x. F of x minus L is less than epsilon. And I may have to make these epsilons So actually, maybe I'll leave this blank for a second. So I may need to make this into something I may need to change. So this is less than this. Okay, and I'll leave a little space here. We also have the same statement for G. And so I have here, let delta 2 equal something which is greater than 0. Then oops. Then oops. X minus a, an absolute value being less than delta 2 implies eventually f of x minus m, g of x minus m is less than something. Okay. Then at the end, I want let delta equal something, which will probably involve delta 1 and delta 2. Usually it's the minimum of delta 1 and delta 2. Because if I have several of these, I want to take the minimum of them. Then if x is between, oops, if x is between, oh, stop that. It's between, if x minus a is between 0 and delta, then I want f of x, g of x minus lm to eventually be less than epsilon. Then I'm done. Okay, so, well, let's try to somehow make this a true statement. So somehow I want to fill in things. So let this equal, I have a problem here. I have like two things. I have an f of x and a g of x. So there are two things that are varying. And so because there's two things that's varying, I'm hard pressed to know what's going on. So what I should do is fix one of them. What do I mean by that? Well, and I don't care which one I'm going to fix. Maybe I'll call this m. So what I'll do is I'll add and subtract the f of x times m. And so I've done nothing. But this is less than or equal to, well, this first term, which is something involving f of x, g of x, minus f of x, m. And then the second part is, well, again, I'm just using triangle equality, f of x, m, minus lm. So now let me factor out f of x. So what remains is g of x minus m. Oops. Okay. So this is g of x minus m. Next, factor out m. So this is m f of x minus l. Oops, why do I do that? So now, if I look at this, let's try to do something here. I have here an m, and I have here f of x minus L. Oh, so if I was able to somehow make some statement so that I can get an epsilon, maybe an epsilon over 2, so that eventually this becomes epsilon. So if I can make some statement so I get an epsilon over 2 here, then I'm okay. So I want that this should be, well, if this is an m, then this should be epsilon over 2m. But again, you can't have that. So maybe what I'll do is put a 2m plus 1. Just make it a little bit bigger so that basically this is less than epsilon over 2. So if I look here, my epsilon here should be epsilon over 2m plus 1. Okay. And this delta is, well, whatever delta is. So then I can just move these over. Oops. There. Whatever. Okay. Here it is. Okay, so that's how I deal with this guy. But now the question, so I've been able to deal with this guy here. Now the question is, how can I deal with this guy? Well, this is fine. I can bound, if I can bound this, then I'd be okay. So I need to bound this somehow. And so I somehow have got to bound this guy here. And so now what I can do is, well, maybe I can't bound this for all x's, but maybe I can bound this for some small x's. So what I should do here is maybe also make this a true statement. So maybe this is going to be, I guess there's going to be like 3 of these. So then I'll have, there is some delta, oops, 2. I guess this is a delta 3 here. So there is some delta 2. So that if x minus a between 0 and delta 2, then f of x minus L is, let's say, less than 1. I can make a bound of 1. So I can just make some sort of arbitrary bound like 1. Okay. Then this says that f of x is between these two. Okay. And so I have that f of x is between, maybe I should make that smaller. I have that f of x, oops, is between L minus 1 and L plus 1. And so absolute value of f of x is less than absolute value of L plus 1. So I can bound it by something like L plus 1. I should put an X here. So I can bound this by L plus 1. And so this should be epsilon over 2 L plus 1. Then when you multiply this bound for this and this bound for this, you're going to get another epsilon over 2. So this is, I'll just say epsilon over 2. I don't have any room. Which gives me an epsilon. So let's tie this all together. So now, so how do I figure this out? Well, I just sort of start at the beginning, figure out what I need, and then write down the end, and then figure out what I need in between. Okay, and so that's the route. Okay, so let me do this. I don't need any of this stuff anymore, I don't think. Okay, so now let's start the proof. Oh, I see that somehow I there's my bound right there. Okay, so let's do this. Since the limit as x approaches a of f of x is equal to L, then given epsilon greater than 0, there exists a delta 1 greater than 0, such that if the absolute value of x minus a is in between 0 and delta 1, then the absolute value of f of x minus L is less than 1. Well, let's probably try to figure out this bound here. Oh, no, we'll figure out that bound in a minute. And there exists a delta 2 such that if x minus a in absolute value is between 0 and delta 2, then the absolute value of f of x minus L is less than 1/2 epsilon over 1 plus absolute value of m. Since the limit as x approaches a of g of x is equal to m, then there exists a delta 3 greater than 0, such that if x minus a in absolute value is in between 0 and delta 3, then g of x minus m in absolute value is less than 1/2 of epsilon over 1 plus absolute value of L. That delta equal delta 1, the minimum of delta 1, delta 2, and delta 3. Certainly, this is greater than 0 since each of the deltas are greater than 0. And so, if x minus a in absolute value is between 0 and delta, the absolute value of f of x minus Lm is equal to the absolute value of f of x times g of x minus f of x times m plus f of x times m minus Lm. And that's because these cancel. So I've just added, subtracted the same thing. So I've done nothing. But now I can group these first two and these last two. So this is equal to the absolute value of f of x times g of x minus f of x times m plus f of x m minus Lm. From this first grouping, let me factor out what's in common, f of x. So this is just equal to f of x times the quantity, g of x minus m. From the second quantity here, let me factor out what's in common, m. So this is just equal to m times the quantity, f of x minus L. Now let's use the triangle inequality. And so this is less than or equal to the absolute value of the first plus the absolute value of the second. So this is less than or equal to the absolute value of f of x times the quantity g of x minus m. By the properties of absolute value, you can just take the absolute value of each of these in the product. So this is less than or equal to the absolute value of f of x times the absolute value of g of x minus m. Plus, again, I'll take the absolute value of this. And by the properties of absolute value, I can just, this is the same as the absolute value of what's inside of each of these each of these terms in the product. So this is plus the absolute value of m plus the absolute value of f of x minus l. Well, f of x is equal to f of x minus l plus l. By the triangle inequality, this is less than or equal to the absolute value of f of x minus l times the absolute value of l. Absolute value of g of x minus m is less than epsilon over 2 times 1 over 1 plus the absolute value of l. Absolute value of m is just absolute value of m. The absolute value of f of x minus l is less than, so long as you're in these intervals, which we are, since x minus a in absolute values between 0 and delta. So it's, and the delta is the minimum of delta 1, delta 2, and delta 3. And so I have that f of x minus l in absolute value is less than epsilon over 2 times 1 over absolute value of m. And so now, well, let's try to simplify this. We already know that, well, however this is, that absolute value of m over the 1 plus absolute value of m is less than 1. So this is less than epsilon over 2. Next, since x minus a in absolute value is between 0 and delta, then it's between 0 and delta 1. Therefore, f of x minus l in absolute value is less than 1. So this is less than 1. So so this guy here is less than 1. Therefore, this whole quantity here is less than 1 plus absolute value of L. And so these are going to cancel. So I get that this is equal to epsilon over 2 plus epsilon over 2, which is epsilon. Therefore, I've shown that the limit as x approaches a of f of x times g of x is equal to L times m. Any questions about that? This one certainly was not an easy, obvious proof. So this one, any questions? People are probably somewhat overwhelmed by this proof. Any questions about this proof? Okay. Think about it. And then if you have any questions tomorrow, we can always go over this proof yet again. Even though no matter how many times I do it, always it's sort of going to look the same, no matter what. Okay, let's show that the limit of a reciprocal is the reciprocal of the limit, so long as you're not dividing by 0. So let's see. Whoa, 8 minutes. We can do it in 8 minutes. Okay, so let's do this. Since the limit as x approaches a of g of x is m, and m is not 0, then, well, I'm going to, then there exists a delta 1 greater than 0, such that if x minus a is between 0 and delta 1, then g of x minus m in absolute value is less than epsilon. I'm going to let epsilon be 1/2 absolute value of m. So this will stand for my epsilon. Well, let's try to simplify this. Absolute value of m is equal to absolute value of m minus g of x plus g of x. The g of x's cancel. So I've really done nothing. I've just added and subtracted the same thing. By the triangle inequality, I have that this is less than or equal to the absolute value of m minus g of x plus the absolute value of g of x. Now, of course, the absolute value of a negative number is the same as the absolute value of the number. And so I can switch around what's inside the absolute value, and that's not going to change because all I'm doing is changing the sign, and well, the absolute value gets rid of the sign change. So this is the same. So the absolute value of m minus g of x is the same as the absolute value of g of x minus m. Of course, these are the same, so plus the absolute value of g of x. Now, I'm assuming that if x minus a is less than delta 1, then g of x minus m in absolute value is less than 1/2 absolute value of m. So this guy here is less than 1/2 absolute value of m. Subtract 1/2 absolute value of m from both sides of your inequality. So I have that 1/2 absolute value of m is less than absolute value of g. So let's write it this way. So so the absolute value of g is greater than 1/2 times the absolute value of m. Since the limit as x approaches a of g of x is m, and m is not equal to 0, then given epsilon greater than 0, and since m is not equal to 0, I'm going to let my new epsilon be 1/2 m squared epsilon, which again is greater than 0, since m and epsilon are greater than 0. Well, since m squared and epsilon are greater than 0. So there exists a delta 2 greater than 0, such that if x minus a in absolute value is between 0 and delta 2, there it is, between 0 and delta 2, then the g of x minus m in absolute value is less than 1/2 m squared epsilon. Let delta be the minimum of delta 1 and delta 2. Then certainly delta is greater than 0, since both delta 1 and delta 2 are greater than 0. And so if x minus a in absolute value is between 0 and delta, then the absolute value of g of x minus m in absolute value is less than 1/2 m squared epsilon. And we also have that g of x is greater than 1/2 times the absolute value of m. So divide, since m here is not equal to 0, we never want to divide by 0, and then the absolute value here is greater than 0. And so g of x is greater than 0. And so I can divide both sides of my equation by the absolute value of m. Or I guess I'll divide both sides of my equation by 1/2 absolute value of m and by g of x. And so I have that 1 over absolute value of g of x is less than 2 over absolute value of m. So now we're almost done. the absolute, so 1 over g of x minus 1 over m in absolute value is equal to m minus g of x divided by g of x over m, all in absolute value. All I did is get a common denominator. So I multiply and divide this first term by m, the second term by g of x, and combine my numerators, write it all over the same common denominator. And so I have here that this is equal to, well, let's look at the numerator, the absolute value of g of x minus m. Remember that it doesn't matter if I switch the order of these, because that just changes the sign. But since I'm taking the absolute value, that doesn't matter. I'm dividing by m here. And so this is 1 over the absolute value of m. I'm dividing here. In the denominator, I have g of x. So this is 1 over absolute value of g of x. Well, 1 over the absolute value of g of x is just less than 2 over absolute value of m. Absolute value of g of x minus m is less than 1/2 m squared epsilon. The 2's cancel, the m squares cancel. So all I have remaining is epsilon. Lecture yesterday. Okay. So now let me proceed to something slightly different. Oh, so here is where we ended up last time. Okay, so proof number 4. So property 4 is that the limit of a quotient is the quotient of the limits, so long as you're not dividing by 0. And so long as that limit in the denominator, the limit of g of x, is not 0. So since the limit as x approaches a of g of x is equal to m, and since m is not equal to 0, then 1/2 times the absolute value of m is greater than 0. So I can make epsilon be this 1/2 times the absolute value of m. That's a valid value of epsilon. So I can find a delta 1. So there exists a delta 1. Oh, I can't do that. There exists a delta 1 greater than 0, such that x minus a in absolute value between 0 and delta 1 implies that g of x minus m in absolute value is less than 1/2 absolute value of m. By the way, notice what I'm doing here is really combining what we did in the last 2 proofs. So the absolute value of m is equal to the absolute value of m minus g of x plus g of x. So just like before, I added and subtracted g of x. So by the triangular inequality, this is less than or equal to the absolute value of m minus g of x plus the absolute value of g of x. Of course, switching around, changing the sign inside an absolute value does nothing. So this is equal to the absolute value of g of x minus m plus the absolute value of g of x, which is less than, well, from above inequality, this is less than 1/2 absolute value of m plus the absolute value of g of x. Subtracting 1/2 absolute value of m from both sides of my inequality, I get that 1/2 times the absolute value of m is less than the absolute value of g of x. Therefore, every quantity here is greater than 0. And so I can take reciprocals. So 1 over the absolute value of g of x is less than 2 over the absolute value of m. Since the limit as x approaches a of f of x is equal to L and m is not equal to 0, then given epsilon greater than 0, we have that 1/4 times the absolute value of m times epsilon is greater than 0. And so this is a valid epsilon that we can use in our epsilon delta definition of limit. So there exists delta 2 greater than 0, such that x minus a in absolute value between 0 and delta 2 implies that f of x minus L in absolute value is less than 1/4 times the absolute value of m times epsilon. Also, since epsilon is greater than 0 and m is not equal to 0, we have that epsilon over 4 times m squared divided by the quantity 1 plus the absolute value of L is greater than 0. All the quantities here in that fraction, that rational expression, are all positive. Oh, well, actually, non-negative. Well, positive here, non-negative here, therefore positive here. So all these numerators and denominators, let's say it that way, all the numerators and denominators are positive. And since the limit as x approaches a of g of x is m, then there exists a delta 3 greater than 0, such that x minus a in absolute value between 0 and delta 3 implies that g of x minus m in absolute value is less than 1/4 times m squared divided by the quantity 1 plus the absolute value of L times the quantity epsilon. Let delta be the minimum of delta 1, delta 2, delta 3. Well, each of these are positive, so delta is greater than 0. And so x minus a in absolute value between 0 and delta implies that x minus a in absolute value is between 0 and delta 1. Thus, 1 over absolute value of g is less than 2 over the absolute value of m. And x minus a in absolute value between 0 and delta implies that x minus a in absolute values between 0 and delta 2. And so by the above, we have that this implies that f of x minus L in absolute value is less than the absolute value of m over 4 times epsilon. X minus a in absolute value between 0 and delta implies that x minus a in absolute value is between 0 and delta 3. And so by above, we have that in this region. The g of x minus m in absolute value is less than 1/4 times m squared divided by the quantity, well, 1/4 m squared epsilon over the quantity 1 plus the absolute value of L. So we can tie these all together now in one big happy inequality. So x minus a in absolute value between 0 and delta implies that, well, this is what we want to bound by epsilon. F of x over g of x minus L over m in absolute value is equal to, let's add and subtract the same quantity. F of x over g of x minus L over g of x plus L over g of x. So these quantities just cancel out. Minus L over m, all in absolute value. By the triangle inequality, this is less than or equal to, well, the absolute value of f of x minus, I'm sorry, f of x, so this is less than or equal to f of x over g of x minus L over g of x, all in absolute value, plus L over G of X minus L over M, all in absolute value. Well, I can factor out 1 over G of X. So this is equal to, well, 1 over the absolute value of G of X. And I can factor out it. L. Oh, and let's do the common denominator. Absolute value of M times the absolute value of G of X. So then we'll just get the numerator. And so this is equal to, well, what I factored out, 1 over the absolute value of G of X times, well, what remains, f of x minus L in absolute value, plus, factor out my L, plus the absolute value of L divided by the common denominator, the absolute value of M times the absolute value of G of X, times, well, the numerator. So you just multiply and divide by M, multiply and divide by G of X. And so times M minus G of X, all in absolute value. Of course, it doesn't, changing the sign inside the absolute value doesn't change anything. Doesn't change what it's equal to after you take the absolute value. Well, from above, we've bounded 1 over the absolute value of G of X by 2 over the absolute value of M. So this quantity here is less than 2 over the absolute value of M. Put a bound here of, well, absolute value of M over 4 times epsilon. And then, well, this remains the same. So plus absolute value of L over absolute value of M. This, well, it's the same as that. So this is, so 1 over absolute value of G of X is less than 2 over the absolute value of M. And then we put a bound on this guy, that this is less than 1/4 M squared epsilon over 1 plus the absolute value of L. And lots of things cancel. So the M's cancel. 2 of these cancel. So you just get epsilon over 2. Well, 2 can't, so 4 divided by 2 is 2. The M squared canceled with these 2 M's. Well, these 2 absolute values of M's. The absolute value of L over 1 plus the absolute value of L is less than 1. And so this whole quantity here is less than epsilon over 2. Oh, I didn't do that. I did it in 2 steps. So this is an epsilon over 2. And what remains is your absolute value of L over 1 plus the absolute value of L. And I know that the absolute value of L over 1 plus the absolute value of L is less than 1. And so I have that this is less than epsilon over 2. We still have this other plus epsilon over 2. And so this whole quantity is less than epsilon. And that's what I wanted to show. Any questions about this? So I just combined what we had done in the previous theorems all together in one theorem. So in the previous 2 theorems, I combined them to look at it all in sort of one bigger theorem. Okay, let me do property 5. And so property 5 says that the limit of a constant times a function is that constant times the limit of the function. Which of course, we've already proven because we've proven that the limit of a product is the product of the limits. And so if, the one quantity we're looking at is trivial, it's always that my function is always just equal to some constant c, then that's what this theorem or this property says. But let's assume that we don't know that, because it'll still be actually fairly easy to prove. And I want to show you how to prove it, assuming none of those other properties that we've proven previously, so that you'll know how to prove it on like an exam. So that's really the reason I'm doing it. And also the fact that if you see these done 50 times over and over again, eventually they sink in that everything that we keep doing is really the same thing. So since the limit as x approaches a of f of x is equal to L, then given epsilon greater than 0, I can let my epsilon in the definition be epsilon over 1 plus absolute value of c, which is greater than 0. So there exists a delta greater than 0 such that x minus a in absolute value between 0 and delta implies that f of x minus L in absolute value is less than epsilon over 1 plus absolute value of c. Well, therefore, if x minus a is between, in absolute value, is between 0 and delta, then c f of x minus cl in absolute value is equal to, factor out what's in common, c times the quantity f of x minus L, all in absolute value, which is equal to, by the properties of absolute value, the absolute value c times f of x minus L in absolute value, which is less than, well, absolute value c is equal to absolute value c, but we have, under the assumption, bounded absolute value of f of x minus L by epsilon over 1 plus absolute value c. So this quantity is less than this. But now, let me rewrite this as absolute value c over the quantity 1 plus absolute value c, all times epsilon. Well, I know that this quantity here is less than 1. Therefore, this quantity here is less than epsilon. And that's what you wanted to show. Any questions about that? So now you look at that, and hopefully you should see, oh yes, everything that I just did on that proof looked very familiar, like we've done it 20 times, because we have. Okay, so let's prove the last of these properties. So this was a gigantic theorem. And so this is the very last part of this gigantic theorem. So we want to prove in this last part that the limit of a difference is the difference of the limits. Since, and basically the proof will be identical to the proof that the limit of a sum is the sum of the limits. It won't really be any different at all. Since the limit as x approaches a of f of x is equals L, then given epsilon greater than 0, obviously epsilon over 2 is greater than 0. So that will be our epsilon that I'm going to be using. So since epsilon over 2 is greater than 0, then there exists a delta 1 greater than 0, such that x minus a in absolute value between 0 and delta 1 implies that f of x minus L in absolute value is less than epsilon over 2. And we're going to do the same thing here. Since the limit as x approaches a of g of x is equal to m, then since epsilon is greater than 0, then epsilon over 2 is greater than 0. So since epsilon over 2 is greater than 0, there exists a delta 2 greater than 0, such that x minus a in absolute value between 0 and delta 2 implies that g of x minus m in absolute value is less than 1/2 epsilon. Let delta equal delta 1, the minimum of delta 1 and delta 2. And so, since both delta 1 and delta 2 are greater than 0, then delta is greater than 0. And x minus a in absolute value between 0 and delta implies that x minus a in absolute value is between 0 and delta 1. X minus a in absolute value is between 0 and delta 2. So f of x minus L in absolute value is less than 1/2 epsilon, and g of x minus m in absolute value is less than 1/2 epsilon. Therefore, we have the following. The quantity the quantity f of x minus g of x minus the quantity L minus m in absolute value is equal to, let's regroup everything, the quantity f of x minus L minus the quantity g of x minus m in absolute value, which is less than or equal to, well, by the triangle inequality, this is less than or equal to f of x minus L in absolute value plus g of x minus m in absolute value. But each of these are less than epsilon over 2. So this is less than epsilon over 2 plus epsilon over 2, which is epsilon. And that's what you wanted to show. So we're done with that huge theorem. So this huge theorem, well, I'll just sort of summarize what the huge theorem says. So the huge theorem basically says that, well, we'll prove some additional things, but it basically says that to find a limit, just plug in and see if you get an answer. If you do, then, and you're not dividing by 0, doing anything weird, then that's a limit. We haven't done roots yet or exponents, but we will in a second. But that's really what it says. It just says, well, plug in. So that's really going to be the technique that we're going to be using. And we'll be doing that back in section 1.6. So using this big theorem to simplify all the limits that we want to take. Theorem. If the limit as x approaches a of f of x is equal to L, with L not equal 0, and the limit as x approaches a of g of x is equal to 0, then the limit as x approaches a of f of x over g of x does not exist, or it could equal plus infinity or minus infinity. So if you have something that's bounded, not equal to, and it doesn't go to 0, divided by something going to 0, then this whole quantity will go to plus infinity. Well, let's see, let's look at the one-sided limit. Let's look at one-sided limits first, because they always exist. So if this quantity, the numerator, does not go to 0, but the denominator goes to 0, then each of the one-sided limits will either go to plus infinity or to minus infinity. The two-sided limit can either go to plus infinity, minus infinity, or it could not exist, because maybe one side limit goes to plus infinity and the other sided limit goes to negative infinity. And so the two-sided limits won't exist because the one-sided limits go to different quantities. Now, there is an arbitrariness when people say does not exist, sometimes they say it doesn't exist if a limit goes to infinity. I usually say that the limit exists and it goes to infinity, rather than having that if a limit goes to infinity, we say it doesn't exist. But please note that some authors, some books will say that the limit doesn't exist if the limit goes to infinity. And so if I go to either plus infinity or minus infinity, I say that that's what the limit is. And if it doesn't actually, the two-sided limits don't go to the same quantity, or or the two one-sided limits don't go to the same quantity, or maybe the one of the one-sided limits doesn't exist, then only in that case do I say it does not exist. Okay, so let's show this. So if the limit is x approaches a if f of x is L, not equal to 0, and the limit is x approaches a of g of x is 0, then the limit as x approaches a of f of g of x does not exist. When I prove this, I'm not going to care about that. I'm just going to say not exist. So even though I said, now I'm contradicting myself. So even though I said before that I worry about if it's plus infinity or minus infinity, here I'm just going to show it doesn't exist. Meaning that if it's infinity or minus infinity, I'll say that that means it doesn't exist. So let's try to prove this by contradiction. So let's suppose that this was false. So let's assume this is true, and suppose that this limit here does exist. Then let's see if we come out with a contradiction. If we do, then, well, the assumptions cannot be valid, meaning that if these hold, then this without the not can't hold. So it has to be a not. Okay, so suppose that the limit did exist. Then there would exist a number k such that the limit as x approaches a of f of x over g of x would equal k. Let's look at 1 plus the absolute value of k. That's greater than 0. So that's a valid epsilon that we can use. Since the limit as x approaches a of f of x over g of x is k, then, given this epsilon, there exists a delta 1 greater than 0, such that x minus a in absolute value between 0 and delta 1 implies that f of x over g of x minus k in absolute value is less than 1 plus the absolute value of k. Next, given epsilon greater than 0, epsilon over 3 is greater than 0, so I can use epsilon over 3 as my epsilon in the epsilon delta definition of limit. Since the limit as x approaches a of f of x is equal to L, then given epsilon over 3, there exists a delta greater than 0, such that x minus a in absolute value between 0 and delta 2 implies that f of x minus L in absolute value is less than 1/3 epsilon. Let's do the same thing, but let's do a different epsilon. Since 1/3 times 1 over 1 plus the absolute value of k times epsilon is greater than 0, then this is a valid epsilon that I can use in my epsilon delta definition of limit. And since the limit as x approaches a of g of x is equal to 0, then there exists a delta 3 greater than 0, such that x minus a in absolute value between 0 and delta 3 implies that f of x minus 0 in absolute value is less than 1/3 times 1 over the quantity 1 plus the absolute value of k. That's the whole, my whole denominator, times epsilon. Let delta equal the minimum of delta 1, delta 2, and delta 3. Since delta 1, delta 2, and delta 3 are positive, then delta is positive. And x minus a in absolute value less between 0 and delta implies that f of x over g of x, okay, implies that, why doesn't that go away? There. Implies that, so f of x over g of x minus k in absolute value is less than 1 plus absolute value of k. So we also have from the above that f of x minus L in absolute value is less than 1/3 epsilon. And by above, we also have that the absolute value of g, well, when I said it above, it was g of x minus 0 in absolute value, which is the same as the absolute value of g, is less than 1/3 times epsilon over the quantity 1 plus the absolute value of k. And so absolute value of L, let's add and subtract things, is equal to, well, I add and subtract f of x, so I'm not doing anything. I add and subtract g of x times k. So by the triangle inequality, well, so this is equal to, so the absolute value of L is equal to the absolute value, well, is equal to L minus f of x plus f of x minus g of x k plus g of x k, all in absolute value, which by the triangle inequality is less than or equal to L minus f of x in absolute value plus f of x minus g of x times k, all in absolute value, plus the absolute value of g of x times k. Again, I can change the sign inside the absolute value, and well, the absolute value of that's not going to change. And so this is equal to the absolute value of f of x minus L plus, let me factor out absolute value of g of x, plus the absolute value of g of x times the absolute value of the quantity f of x over g of x minus k, plus, again, I can take the absolute value. The absolute value for product is a product of the absolute values. And so this is equal to the absolute value of g of x times the absolute value of k. Well, we notice that absolute value of f of x minus L is less than 1/3 epsilon. The absolute value g of x is less than 1/3 epsilon over the absolute over the quantity 1 plus absolute value of k, and at this, that the absolute value of f of x over g of x minus k is less than 1 plus the absolute value of k. And just like before, we had that, so plus the absolute value of k is less than 1/3 times epsilon over 1 plus absolute value of k, and the absolute value of k is still the absolute value of k. So this is epsilon over 3. That remains the same. The 1 plus absolute value of k's cancel. So this again, this second term is epsilon over 3. And this is, well, this is an epsilon over 3 times absolute value of k over the quantity 1 plus the absolute value of k. I know that the absolute value of k over 1 plus the absolute value of k is less than 1. And so this is less than epsilon over 3. So if you add these all up, this is less than epsilon. But this says that absolute value of L is less than epsilon for all epsilons. That means that, well, if the absolute value of some number is always less than any number, all positive numbers, that means that that number, that fixed number, must be 0. And so L must be 0. But our assumption here is that L is not 0. So we have a contradiction. So I have this contradiction here that L is not 0. And so we have here that L is equal to 0. So this contradicts our assumption. Therefore, the limit as x approaches a of f of x over g of x can't exist. It can't be a real number. And so I'm done. Okay. Any questions about this? Any questions? Oh, I just saw a, okay. So someone put up so if you look in your chat box, I noticed someone just put up a URL for studying groups. And so if you wish to join that group, you can do that. Any questions on this proof? Okay. So next. As I said before, well, we were able to do show that the limit as x approaches a of x is equal to a. And I was able to show the limit as x approaches a of f of x times g of x is the limit as x approaches a of f of x times the limit as x approaches a of g of x. So with that, we should be able to prove, well, that implies that the limit as x approaches a of x squared is a squared. But let me not do that. So yes, that does work. Yes, we've actually shown this. But again, I'm going to assume that you don't know that. I'm going to assume that we're going to prove this from basic concepts. So let me not use any of the previous theorems that I've proven. Let me just prove this from the epsilon delta definition. So my theorem, limit as x approaches a of x squared is a squared. Given epsilon greater than 0, epsilon over 1 plus 2 absolute value of a is greater than 0. Let delta be the minimum of 1 and epsilon divided by the quantity 1 plus 2 absolute value of a. Well, each of those are greater than 0. So delta is greater than 0. By the way, the fact that I chose 1 is arbitrary. I could have chosen anything, but if you choose 1, it makes determining this quantity easier. So a lot of times you can do a bound and your bound is arbitrary. But when a bound is arbitrary, we choose 1 because usually 1 is the easiest number to deal with. It gives us nicer numbers to deal with. Okay, so delta here is greater than 0. X minus a in absolute value between 0 and delta implies that, well, from here, x minus a in absolute value is less than epsilon over 2. So the absolute value of x minus the absolute value of a is less than or equal to the absolute value of x minus the absolute value of a. Note that we're just saying if you take any number, it's always less than its absolute value. Well, that's kind of horrible. I'm holding on to 3 things, so it didn't write very well. I'm just saying here that if you take any number, it's always less than its absolute value. 8, less than or equal to, is less than or equal to 8. Negative 12 is less than or equal to 12. So no matter what, so if it's positive, then it's going to actually be equal. But if it's a negative number, then it's going to be less than. If it's 0, it's also equal. And so no matter what, we have that if you take something, if you have a quantity, then it's always less than or equal to its absolute value. And so, oops. The absolute value of x minus the absolute value of a is less than or equal to the absolute value of x minus the absolute value of a, all quantity in absolute value, which is less than or equal to x minus a in absolute value. But by this assumption here, this is less than 1. Therefore, adding absolute value of a to both sides of your inequality, I have that the absolute value of x is less than 1 plus absolute value of a. So now, assuming that this is true, that x minus a in absolute values between 0 and delta, we have that x squared minus a squared in absolute value is equal to, factoring what's inside the absolute value, x minus a times x plus a in absolute value. So that's just a well, one of the special product formulas, the difference squares formula. And so by the properties of absolute value, the fact that the absolute value of a product is the product of the absolute values, this is equal to absolute value of x minus a times the absolute value of x plus a. Well, by the triangle inequality, the absolute value of x plus a is less than or equal to the absolute value of x plus the absolute value of a. We have that x minus a in absolute value is less than, oops, epsilon over 1 plus 2 absolute value of a. We have that absolute value of x is less than 1 plus the absolute value of a. And so 1 plus the absolute value of a plus another absolute value of a is 1 plus 2 absolute value of a. So these guys cancel. So all I have remaining is epsilon. And that's what you wanted to show. So we're done. Any questions about that? Any questions? Oops. Any questions about that? Okay, let's do it for cubes. So again, obviously, if we've shown it for, you know, the first power and for the second power, then the fact that we show that limit of the product is product of limits, then obviously this is true for the third power. But again, let's assume that we don't notice that. We've actually already proven this. So let's do this from basic, like, you know, from the epsilon delta definition. So this is how, of course, you would do it in an exam setting. So the limit as x approaches a of x cubed is a cubed. Given epsilon greater than 0, we have that epsilon over 3a over the quantity 3a squared plus 3 absolute a plus a is greater than 0. So we can make this quantity here in epsilon in our definition of epsilon delta definition of limit. Let delta equal the minimum of 1 and epsilon over 3. Oh no, I guess this is going to be part of my epsilon. This is going to be part of my delta. So sorry about that. That's part of my delta. And so let delta be the minimum of 1 and epsilon over the quantity 3a squared plus 3 absolute a plus a. Well, each of these are greater than 0. Therefore, delta is greater than 0. So x minus a in absolute value between 0 and delta implies that absolute value of x minus absolute value of a is less than or equal to absolute value of x minus absolute value of a, all in absolute value, which is less than or equal to absolute value of x minus a, which by this assumption is less than 1. So again, adding absolute value of a to both sides of my inequality, I have that absolute value of x is less than 1 plus the absolute value of a. We also have the fact that this is less than delta, so this is less than, so the absolute value of x minus a is less than epsilon over the quantity 3a squared plus 3 absolute a plus 1. So the x minus a in absolute value is less than epsilon over the quantity 3a squared plus 3 absolute a plus 1. So let's look at x cubed minus a cubed in absolute value under the assumption here that x minus a is between 0 and delta. Well, just like before, let's factor this. And so by the special product formula, the difference of cubes, I have that x cubed minus a cubed is equal to x minus a times the quantity x squared plus ax plus a squared. And so by the properties of absolute value, the fact that the absolute value of a product is a product of the absolute values, this is equal to absolute value of x minus a times the x squared plus ax plus a squared, all in absolute value. Well, by the triangle inequality, we have that this is less than the absolute value of x squared, which is just x squared, plus the absolute value of a times the absolute value of x, plus the absolute value of a squared, which is just a squared. This is going to be less than, well, I know that x minus a in absolute value is less than epsilon over the quantity 3a squared plus 3 absolute a plus 1. I know that absolute value of x, maybe I should put an absolute value there. The absolute value of x is less than 1 plus absolute value of a. And so x squared is less than 1 plus the absolute value of a quantity squared. And I have here that absolute value of x is less than 1 plus absolute value of a. So let's simplify this. So this stays the same, this first quantity. Let's use the special product formula, the perfect square trinomial formula. So 1 plus the absolute value of a squared is the absolute value of a squared, which is a squared, plus 2 times the absolute value of a, plus 1 squared, which is 1. Let's multiply the absolute value of a inside the parentheses. So absolute value of a times absolute value of a is a squared. Absolute value of a times 1 is the absolute value of a. And then we have this last term here, a squared. So now let's, well, these are going to be the same. I have 1, 2, 3 a squares. I have 2, 3 absolute values of a, and I have a 1. But the numerator and this quantity cancels. And so the denominator, I'm sorry, this denominator cancels with this quantity here. And so we just have the numerator epsilon. And that's what we wanted to show. Any questions about that? Okay, so let's show this. The limit as x approaches a of x to the n equaling a to the n for all natural numbers n. So we do this, we keep doing the same thing. We've shown it for x to the first power. I've shown it for x to the second power. I've shown it for x to the third power. Well, it has to work in a similar fashion for each of the powers. I guess we're going to have to try to prove this using mathematical induction. Oh, actually. Oh. This is mathematical induction. I'm doing it with little dots. Okay, so I'm sort of hiding my mathematical induction. Okay, so I should have done this by mathematical induction, but I guess I was lazy. So given epsilon greater than 0, let delta be the minimum of 1 and the quantity epsilon divided by the quantity 1 plus the absolute value of a quantity to the power n minus the absolute value of a to the power n. Then delta is greater than 0. This is greater than this. And so the denominator is positive and the numerator is positive. So this quantity is positive and this is positive. Therefore, the minimum of these is positive. X minus a in absolute value between 0 and delta implies that, well, let's look at this one guy first, that x minus a in absolute value is less than 1. Let's do what we've done before. So x minus, I could have also done this using the, and this is what I'm really doing. I'm doing the inverse triangle inequality. And so x minus the absolute value of x minus the absolute value of a is less than or equal to the absolute value of x minus the absolute value of a in absolute value, which is less than or equal to the absolute value of x minus a, which is less than 1, So add the absolute value of a to both sides of your inequality. So absolute value of x is less than 1 plus the absolute value of a. We also have, from the fact this is epsilon, delta, that x minus a in absolute value is less than epsilon over the quantity 1 plus the absolute value of a, all quantity to the n minus the absolute value of a to the n. Well, x to the n minus a to the n in absolute value is equal to, you can factor. So it's the same special product formula. Or you can use synthetic division. So this is equal to the absolute value of x minus a times the quantity x to the n plus a x to the n minus 1, x to the n minus 1 plus a x to the n minus 2 plus a squared x to the n minus 3 plus a to the n minus 1. Well, let's use the triangle inequality. So this is less than or equal to the absolute value of x minus a times the quantity, absolute value of x to the n minus 1 plus the absolute value of a times the absolute value of x to the n minus 2 plus the absolute value of a squared times the absolute value of n minus 3 plus plus the absolute value of a to the n minus 1. So this is equal to the absolute value of x minus a times the quantity, the absolute value of x to the n minus the absolute value of a to the n divided by the absolute value of x minus the absolute value of a, which is less than absolute value of x minus a times a, 1 plus the absolute value of a to the quantity n minus the absolute value of a to the n divided by 1 plus the absolute value of a minus the absolute value of a. The absolute values of a's will cancel. So this is just equal to x minus a in absolute value times my numerator. 1 plus the absolute value of a to the power n minus a to the power n. But from here, this is less than epsilon over 1 plus absolute value of a all to the power n minus absolute value of n times, well, the same thing. So these are going to cancel, and all I have remaining is epsilon. And that's what I wanted to show. So we're done. Oh, here I'm going to, so now we're going to do the same thing, but now we're going to use mathematical induction. So there was a little bit of, I would say, hand waving in this. There's a little bit of hand waving here that I did in this proof. I should have really done mathematical induction. I'll show you how to do it with mathematical induction, because I'm going to do the same proof. Obviously, the proof that I'm going to show here works for what I did above. This is just a more general theorem. Limit x approaching a of f of x equal L implies that the limit as x approaches a of f of x to the n is L to the n. And that this works for all natural exponents n. So let's use mathematical induction. Let's show that this works for the initial case when n is equal to 1. Well, obviously it works because that's a restatement of this fact. So let's plug in here n is 1 and see what happens. So the limit as x approaches a of f of x to the power 1 is equal to, well, the limit as x approaches a of f of x. But we're assuming that this is equal to L. So this is equal to L, but L is equal to L to the first power. So therefore, I've shown that this, the limit as x approaches a of f of x to the power 1 is L to the 1. And that's what I wanted to show. I wanted to show that the limit as x approaches a of f of x to the n is L to the n when n is 1. So I've shown the initial case. Now let's do the induction case. So we're going to assume that, so let's recall what mathematical induction is, in case you forgot. So mathematical induction is the following. Suppose you have a whole bunch of dominoes. So you have some dominoes, and they're all lined up next to each other. If one domino falling causes the next domino to fall, so if you have one domino and that causes the next domino to fall, and if the first domino falls, so if my first domino falls and every domino that falls causes the next domino to fall, then all dominoes fall. So what I've done here is shown the following, that the first domino fell. Now I want to show that, well, if one domino falls, the next domino will fall. Since the first domino fell and one domino falling causes the next domino to fall, then we would have shown that all dominoes fell. So suppose the limit as x approaches a of f of x to the k is equal to L to the k. K here is an arbitrary natural number exponent. And since we have proven, well, the fall, oops. Sorry, I'm pointing to the wrong computer. And since we have proven that the limit as x approaches a of f of x equaling L, and the limit as x approaching a of g of x is equal to m, implies that the limit as x approaches a of f of x times g of x is L times m, then we have the following. The limit as x approaches a of f of x to the k plus 1 is, well, let's write an exponent of k plus 1 as, well, an exponent to the first power times exponent to the kth power, using properties of exponents. So this is the limit as x approaches a of f of x times f of x to the k. Well, by the above theorem, the fact that the limit of a product is a product of limits, this is the same as the limit as x approaches a of f of x, which by the assumption of the theorem is L, and times the limit as x approaches a of f of x to the k. But by assumption, that's L to the k. Well, we just have two numbers here that I'm multiplying. And so since they have the same base, I add exponents. So this is L to the k plus 1. Therefore, by the principle of mathematical induction, we have that the limit as x approaches a of f of x to the n is L to the n for every natural number n. And so we're done. Any questions about this? No questions about this? Okay, so now we're going to show, so I've shown that, so this, that now the limit of a function to an exponent, well, the limit of something to an exponent is the exponent of those limits. Now we're going to show that the finite sum of limits, the finite sum of limits is the finite, well, the limit of the finite sum of functions is the finite sum of their limits. There, I said it correctly, finally. Okay, so let me do this. So the limit, if the limit as x approaches a of f sub 1 of x is equal to L sub 1, and the limit as x approaches a of f sub 2 is equal to L sub 2, and the limit as x approaches a of f sub 3 is equal to L sub 3, dot, 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 dot. And the limit as x approaches a of f sub n of x is equal to L sub n. Then the limit as x approaches a of the sum k equaling 1 to n of f sub k at x is equal to the sum k equaling 1 to n of L sub k. And we want to show that this is true for all natural numbers n. So I can, if I add up a finite number of functions and take their limit, that's the same as taking the limit of each and adding up that finite sum of those limits. So let's try to prove this using mathematical induction. So first, I want to show that the first domino falls. So let's show that the first domino falls. So I have here, I want to replace n by 1 in that, the conclusion of my theorem, and show that that works. And so we have here the limit as x approaches a of the sum k equaling 1 to 1 of f sub k at x is equal to the limit as x approaches a of f sub 1 of x. And by our assumptions in the theorem, we have that that's equal to L sub 1, which in your summation notation, that's just equal to the sum k equaling 1 to 1 of L sub k. And so we've actually shown the initial case. We've shown here that the limit as x approaches a of the sum k equaling 1 to n of f sub k at x is equal to the sum k equaling 1 to n of L sub k when n is 1. There's only one term in that summation. So I've shown it for that one term. So the initial case holds. Now let's show that the induction case holds. So I guess I'll replace little n with capital N. So suppose that the limit as x approaches a of the sum k equaling 1 to capital N of f sub k at x is equal to the sum, k equaling 1 to capital N of L sub k. So we'll use the properties that we've shown in the previous theorem, that huge previous theorem. Since we've proven that the limit as x approaches a of f of x equaling L, and the limit as x approaches a of g of x equaling m implies that the limit as x approaches a of f of x plus g of x is L plus m, we have the following. The limit as x approaches a of the sum k equal 1 to capital N plus 1 of f sub k at x is equal to, I'm just going to rewrite this sum as the sum of the first capital N terms plus the last term. So this is equal to the limit as x approaches a of the quantity sum k equal 1 to capital N f sub k at x plus the last term f sub capital N plus 1 at x. Well, by the theorem, the property that we showed, well, it's just the limit of each of these. So we know that the limit of a sum is the sum of their limits. And so this is just the limit as x approaches a of this sum here. But by the induction hypothesis, that's just equal to the sum k equal 1 to capital N of L sub k. The limit as x approaches a of f sub capital N plus 1 at x is just equal to L sub capital N plus 1 by the assumption of the theorem. But this can be written in summation notation as the sum k equaling 1 to capital N plus 1 of L sub k. But now, this says that our induction, that our induction case holds. Therefore, by the principle of mathematical induction, we have that the limit as x approaches a of the quantity sum k equaling 1 to n f sub k at x is equal to the sum k equaling 1 to n of L sub k. And this is true for all natural numbers n. Any questions about that? Okay. So now, finally, we have some things that truly simplify your life. So the next few theorems are like, okay, so now how we calculate these are going to be really, really easy and simple. How we calculate limits. Theorem. If P is a polynomial and if A is a real number, then the limit as x approaches A of P of x is equal to P at A. So if you have a polynomial and you're trying to calculate the limit, all you have to do is plug in the value. And so the finding limits in this case is the same as evaluation. So that's nice. You know how to evaluate from grade school. And so this makes your life really, really easy. So let's prove this. So we've proven the following. Basically, it's just showing you that we've actually done all this. So we've proven the following. We just collect all the facts. So we've proven that for C being a real number, the limit as x approaches A of C times f of x is equal to C times the limit as x approaches A of f of x. And we've shown that for every whole number, exponent, the limit as x approaches A of x to the n, where n is a whole number, is equal to a to the n. Except if, I guess the only one that we haven't shown, I guess there's actually one set if. Both a and n is 0. So we actually haven't shown that. 0 to the 0, because that's something weird. So we've done it. So we've shown all this except for that one weird case. And we'll throw out that weird case because that is a weird case to deal with. Matter of fact, we won't deal with that until calculus 2. So I'm throwing away that case. For n being a natural number, we've shown that the limit as x approaches a of the sum k equaling 1 to n of f sub k at x is equal to the sum k equaling 1 to n of the limit as x approaches a of f sub k at x. So that's what we proved in the previous theorem. So let's look at a polynomial. Let p of x be the sum k equaling 0, a sub k, x to the k. Then the limit as x approaches a of p of x is the limit as x approaches a of the sum k equaling 0 to n of a sub k times x to the k. But this is equal to, from here, the sum k equaling 0 to n of the limit as x approaches a of a sub k x to the k. But from here, I have that this is equal to the sum k equaling 0 to n of a sub k times the limit as x approaches a of x to the k. And so we have from here. So we have from here that this is just a to the k. By the way, in our notation, when we have this sum here, and we have a 0 to the 0, we just sort of assume whatever definition so that it makes the summation work. So sometimes we let it equal 0, sometimes we let it equal 1. Just let it equal 0 and 1 so that it works in the case. So this is the sum k. So I've sort of swept aside. We always sweep aside this case when we're using the summation notation. So this is the sum k equaling 0 to n of a sub k times a to the k. But this is just the polynomial evaluated at a. So if you have a polynomial and you have a limit, just plug in that number. Oh, that makes my life easy. Next theorem. And this is another very important theorem. If q of x is a rational function, and if a is in the domain of q, meaning I'm not dividing by 0, then the limit as x approaches a of q of x is q of a. So this says that to find limits of rational functions, you also just plug in. But if you're dividing by 0, then you have to do something else. So usually the something else means more work. So if you divide by 0, then, well, if you don't divide by 0, then whatever number you get is your answer. Okay, good. And we just had that one little pesky problem of how to deal with when you divide by 0. We actually know one case. If you have something that's not going to 0 in the numerator, but it is going to 0 in the denominator, then the limit doesn't exist or is equal to plus or minus infinity. The one-sided limits will equal plus or minus infinity. And the two-sided limits may equal plus or minus infinity, or it does not exist. So let's try to prove this. Let q of x equal f of x over g of x, where f and g are polynomials. Since a is in the domain of q, then g of a is not 0. We've proven the following. If p of x is a polynomial, and if a is a real number, then the limit as x approaches a of p of x is equal to p of a. That was the previous theorem. In the very big theorem, that one that gave us all the properties of limits, we showed that if the limit as x approaches a of g of x is not 0, then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f of x over the limit as x approaches a of g of x. So let's use these to look at the limit as x approaches a for a rational function. The limit as x approaches a of q of x is the limit as x approaches a of f of x over g of x, which is equal to the limit as x approaches a of f of x over the limit as x approaches a of g of x. By the way, recall that if a is in the domain of g, that means you're not dividing, but if a is in the domain of, I called it q, I'm sorry. If a is in the domain of q, if a is in the domain of q, that means that g of x, the g of a is not 0, which means that in a neighborhood of a, g is also not 0. We proved that yesterday. And so we have that this limit, well, each of these, both the numerator and denominator, they're just polynomials. And so the limit, so I have that the limit as x approaches a of f of x over g of x is the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, which since they're polynomials, this is just equal to f of a over q of, over g of a, which is q of a. And that's what I wanted to show. So how do you evaluate a limit for a rational function? You just plug in the value. If you're dividing by 0, do more work. If you're not dividing by 0, then it's whatever the answer is. So meaning keep doing work until you get something where you're not dividing by 0. And that's a technique for finding limits. So this really tells us our technique for finding limits. Many, most, almost all of our limit questions are questions involving limits from this book are involving rational functions. There are few that aren't, but the vast majority are. Here is a very important theorem. The squeeze theorem, or sometimes we call it the sandwich theorem, I guess, it depending on how hungry you are. So either we'll call it the squeeze theorem or the sandwich theorem. Why do we call it the squeeze theorem? Because suppose you have some function. Okay, and let's do another function. Let's see which is smaller, f. And the bigger one was g. And the guy in between, oh, no, this is, oops. This is h. This is h. And then the very biggest one. Oh, no, that was g. This was g. This is g. This is g of x. And the very biggest one is h of x. Okay, so suppose we have the following. So I have this big function, h of x. So suppose that suppose that g of x, this black curve here, is in between f of x and h of x. Suppose that the limit as x approaches a of h of x is the same as the limit as x approaches a of f of x. So this guy here approaches the same limit as this guy. Then, since g is sandwiched in between these two functions, then this limit here will also exist, and it will equal that mutual value that is being squeezed to take. So that's the squeeze theorem or the sandwich theorem. So suppose f of x is less than or equal to g of x, which is less than or equal to h of x. For every x in some deleted neighborhood of a, then the limit as x approaches a of f of x equaling the limit as x approaches a of h of x, which is equal to, let's say, the number L, implies that the limit as x approaches a of g of x is L. So this implies that the limit as x approaches a of g of x exists. And not only does it exist, it's equal to that mutual value that both the limits of f and the limits of h approached. So let's prove this. Given epsilon greater than 0, since the limit as x approaches a of f of x is equal to L, then there exists a delta 1 greater than 0 such that x minus a in absolute value, such that x minus a in absolute value between 0 and delta 1 implies that f of x minus L in absolute value is less than epsilon. Therefore, using the properties of absolute value inequalities, we have that f of x minus L is between minus epsilon and epsilon. Let's add L to all three sides of my three-part inequality. And so f of x is between L minus epsilon and L plus epsilon. Therefore, L minus epsilon is less than f of x. And let's do this for g of x now, for h of x. So since the limit as x approaches a of h of x is equal to L, then there exists a delta 2 greater than 0, such that x minus a in absolute value between 0 and delta 2 implies that h of x minus L in absolute value is less than epsilon. And so let's again use the properties of the absolute value, the inequality, absolute value inequalities. And so we have that h of x minus L is between minus epsilon and positive epsilon. Let's add L to all three sides of my inequality, of my three-part inequality. Therefore, h of x is between L minus epsilon and L plus epsilon. And so h of x is less than L plus epsilon. Let delta be the minimum of delta 1 and delta 2. Since delta 1 and delta 2 are positive, then delta is positive. So since x minus a is between 0 and delta, then x minus a in absolute value is between 0 and delta 1. Therefore, L minus epsilon is less than f of x. Since x minus a in absolute value is between 0 and delta, then x minus a in absolute value is between 0 and delta 2. Therefore, from the above, we had that h of x is less than L plus epsilon. So suppose that x minus a in absolute value is between 0 and delta. Then we have that L minus epsilon is less than f of x, and h of x is less than L plus epsilon. Therefore, x minus a between 0 and delta implies that, well, we have it. There it is right there. That L minus epsilon is less than f of x. And by the assumption of our theorem, f of x is less than or equal to g of x, which is less than or equal to h of x in our deleted neighborhood. And we also have that h of x is less than L plus epsilon. So let's just write this. So therefore, voila. G of x is between L minus epsilon and L plus epsilon. Subtract L from all parts of this three-part inequality. So G of x minus L is between minus epsilon and positive epsilon. But now let's rewrite this instead of as a three-part inequality, as an absolute value inequality. Therefore, G of x minus L in absolute value is less than epsilon. But that means that the limit as x approaches a of g of x is L. And that's what I wanted to prove. Good. I think. Of a limit. Limit. So problem 20. Limit x approaches 10. 3 minus 4/5 x is equal to -5. Okay, so let's try to prove this. The way that I'm going to prove this is really just sort of using a template. And so I'm just gonna, all the proofs are gonna start out basically the same way. So I'm just gonna write, given epsilon greater than 0, let delta equal. I don't know what delta is. So I'm gonna let it equal something that will be determined at the end after I figure out what it has to equal. Because I don't know at the beginning what it has to equal. I can't look into the future. So I'll just say, well, it's whatever. And it'll somehow be some quantity greater than 0. Such that x minus a in absolute value. Oops. In this case, a is 10. Oops. Oh, okay, that's fine. So someone's just apologizing that their laptop died for a little while. Okay, that's fine. So x minus a, which in this case is 10. So let's assume that x minus 10 is less than my delta. And well, I don't know what my delta is. It's whatever it has to be. This implies that, well, f of x minus, oops, L in absolute value is less than epsilon. So I've got to somehow make this less than epsilon. So let's simplify. So this is equal to 3 minus 4/5 x. Minus and minus become a plus 5. So now let's combine these. And so if I do that, this becomes, well, 3 plus 5 is 8. So 8 minus 4/5 x. Okay, good. Now I want to simplify this. I basically want to make 8 into 10. So let's multiply by 5/4. And then, well, if I multiply by 5/4, I'm going to also have to divide by 5/4. So let's write it this way. So let's do 4/5 times 5/4. Absolute value of 8 minus 4/5 x. So I'm obviously just multiplying by 1. Now let's multiply 5/4 inside the parentheses. Well, 8 divided by 4 is 2, times 5 is 10. The 5s and the 4s cancel, so you just get x. But now, remember that I can change the sign inside the absolute value. And once I take the absolute value, that's not going to change its value, because the absolute value of a negative number is the same as the absolute value of a positive number. And so this is 4/5 absolute x minus 10. Oh, look. Here's x minus absolute value of x minus 10. Here's absolute value of x minus 10. So if this were epsilon, I'd be done. Well, how do I make this epsilon? Well, oops, let's do a, if this x minus 10 absolute value were less than, let's say, 5/4 epsilon, then I'd be happy, because then I could actually just cancel everything out. Okay, so I should make this 5/4 epsilon. And make this 5/4 epsilon. So I go back at the beginning and fill in what I needed. So if I let delta equal 5/4 epsilon, then this quantity here is less than 5/4 epsilon. But then the 5's cancel, the 4's cancel, you just get epsilon. And so you're done. Any questions about that? So notice how this is written up. So it's written up logically, kind of the same way that I wrote up the theorems, the proofs of the theorems, where it was done logically, where you start with one statement and you proceed in a logical procession until you have proven what you wanted to prove. And so I started and I keep progressing till I prove what I wanted to prove. Any questions about this? Okay, so I'm done. Let me do another one. So problem number 22. Oh, by the way. This is with epsilon and deltas. Okay, so let's try to show this. So again, it's saying that we have to prove this using my epsilon and deltas. Okay, so my epsilon and delta proof, a definition of limit. So let's prove this. Oops. Oh, I see. I made it slightly smaller is what happened. Okay, so let's prove this. So I'll start out the exact same way I did before. And so to prove a epsilon delta proof, I will start with given epsilon greater than 0. Let delta equal, I don't know what it should equal. Just like before, I cannot read the future, but I'll leave it blank so that I can fill it in. So let's leave a little space here, greater than 0. Such that if absolute value of x minus a in this case is a negative 1.5, so minus a negative is a plus, is less than, ooh, I hate that, 1.5. So it doesn't look like the one all of a sudden made it look like the absolute value of 5. Okay, so I'll say, oh, I'll make that into where my ones look like that. So if x plus 1.5 in absolute value is between 0 and whatever delta is. So I'll plug in the delta at the end, once I know what I need to make it equal. Then this is going to imply that, well, let's see what I want to end up with. I want that this quantity minus this quantity in absolute value is less than epsilon. So I'll just take this guy minus this guy in absolute value, see what it is, and then simplify it. And so this is 9 minus 4x squared over 3 plus 2x minus a negative minus 6. Okay, so let's do this. Somehow I'm going to have to simplify this. Well, what do you think you should do with a rational expression? What do you think if I gave you this problem, if I just gave you this guy here in algebra 1, or in, preschool, in non-preschool, in junior high, if I gave you that, what would you do? Well, you simplify it. So let's try to simplify this rational expression. I mean, what else do you do with rational expressions? You simplify rational expressions. So let's try to simplify this rational expression. Let's factor the numerator and denominator. And so this is difference of squares. So I'll use the difference of squares, the special product formula, the difference of squares formula. And so 3 minus 2x times 3 plus 2x all over 3 plus 2x minus 6. Oh, okay. So now what can I do? Well, it certainly looks like I can do some cancellation here. I can certainly cancel, because notice that the denominator, the 1 plus 3 halves, is greater than 0, is not equal to 0, because the absolute value is greater than 0. So x plus 3 halves is greater than 0, meaning if you multiply both sides of that inequality by 3, 3 plus 2x is not 0. So I'm not divided by 0, so I'm not canceling zeros. So these are going to be equal. So this is equal to, the absolute value of 3 minus 2x minus 6. But now, well, let's do some simplification. I have here a negative 2x. 3 minus 6 is minus 3. Let's factor out negative 2. Dividing what's inside by negative 2, I get a plus 3 halves. So this is equal to, well, absolute value of negative 2 is just 2. And 3 halves is the same as 1.5. And then you're like, oh, I want this to be less than epsilon. Or, well, let's make it equal here. And then something, so this is less than epsilon. Okay, so I have a 2. Notice here that this quantity here, the absolute value of x plus 1.5, that's the thing that I have a blank here, where if I bound it, I have an arbitrary choice to bound it so that I can, the arbitrariness is that it can be a function of epsilon. So as long as I have some quantity only involving epsilon, then I'm okay. So let's do this. So if this is a 2 here, I'm sorry. If this is a 2 here, and I make this epsilon over 2, epsilon over 2, epsilon over 2, then the 2's cancel, and we get epsilon, and we are done. Any questions about that? Any questions on this proof? So now, if you read this proof, it looks like a very nice proof. It starts, and you can proceed reading from the top to the bottom, and it proceeds in a logical manner. Any questions about this? So some people do it where they start at the end and then they get back to the beginning. But the problem is that students then don't know that they have to completely rewrite the proof where it starts at the beginning, ends at the end. And so I think that this is a better way of doing it, where I put in a blank, where I start at the beginning, end at the end, and then I leave a blank for things I don't know, and then fill them in at the end. If you notice, it was like the very last statement here, almost the very last statement, until I could figure out what to fill in. Any questions about this? Okay. So, oh, this is, oh, here it is, the next one. Problem number 30. So let me do problem number 30. Oh, there's still a few more. Okay, so problem number 30 says the limit as x approaches 2 of x squared plus 2x minus 7 is equal to 1. We're going to proceed the same fashion. So everything's going to be the same as we've done before in the proof. Given epsilon greater than 0. I don't like that greater than, a little squiggly there. Epsilon greater than 0. Let delta equal something, which would be greater than 0, such that if x minus a is less than delta, then a whole bunch of facts. I know I'm going to need some blank space here. Then, well, what do I want to conclude? So my conclusion is that this minus this in absolute value is less than epsilon. So I'll just make this equal sign into a little minus sign and somehow try to bound things so everything works out nicely. So I'll leave some space here. I don't know how much, maybe down to here. So I'll do f of x minus L, which is, I've already forgot, x squared plus 2x minus 7 minus 1. Okay, so let's try to somehow, let's try to somehow bound this. So maybe I'll put it. Let's get rid of the parentheses. So this is just x squared plus 2x minus 7 minus 1. And so this is just x squared plus 2x minus 8. So I have a polynomial. Well, the first thing I want to do is somehow simplify this polynomial. And so I'll factor. So let's factor this into x plus 8 times x minus 2. And so, using the properties of absolute value, this is absolute value of x plus 4 times absolute value of x minus 2. Okay, oh, the x minus 2, I can somehow bound that. So this is good. So let's leave everything in terms of x minus 2. Well, actually, let's do that. Let's write everything in terms of x minus 2. If I do that, that makes my life easier. So this is actually going to be a little different. I think I'm going to do this different than the way I showed it in previously. So, because today is a different day. So I'm going to do it slightly different. So this is equal to, let's rewrite x minus 4 as x minus 2 plus 6. So I can write 4 as 6 minus 2. So this is the same as the absolute value of x minus 2 plus. Oh, I know why I don't want to do that. Oh, I'll still do that. And so this is less than or equal to. So now let's use the triangle inequality. And so by the triangle inequality, this is less than or equal to absolute value of x minus 2 plus the absolute value of 6, which of course is 6. Oops. Why did I put that? That's the absolute value. So now, if I can bound the absolute value of x minus 2, I'd be done. I can just pick an arbitrary number, 5, 10, 50. Okay, so if I said let x minus 2 in absolute value be less than 50, then this would be less than this. If I said I want this to be less than 50, then this would be less than 56. Then I could say, well, let that be less than epsilon over 56, and then we're done. But as I said, I like bounds of 1. Why? Well, it just makes my life easier. So what I'm going to do is make this be less than 1. And so, oops, I accidentally hit that. And so I have that this is less than 1. If I make this the minimum of 1 and something else. And so x minus 2 in absolute value is less than 1. That means I can make this guy here less than 1. But if I do that, then I don't like the way that looks. It almost looks like a 21. Let's do 2. Okay, so then 1 plus 6 is 7. I can now bound the x minus 2 by epsilon over 7. So if I make this epsilon over 7, notice that this minimum is certainly greater than 0. We have that, well, since delta is a minimum of 1 in epsilon over 7, this is less than epsilon over 7. And so I have that x minus 2 is less than epsilon over 7. So this is less than epsilon over 7. The 7's cancel. I get epsilon. So I'm done. Okay. Any questions about that? I could have done this in a slightly different fashion, but actually I think in the lecture notes, it shows it in a slightly different way, but it's good to see it more than one way of doing this. Any questions about this? No? Everyone's good. Okay. So now, oh, right. So if I look here, let's see. So how did I do it? Oh, that's what I did. I did it really weird. I just let I did an arbitrary constant. The arbitrary constant that I used was 5 rather than 1. And everything worked. Of course, then your delta is going to be slightly different. It's epsilon over 11 rather than epsilon over 7. So that was just showing that it really didn't matter the way that we did that. Okay. So next I want to do the cubic. Oh, and then everything else is the same. Okay, then I don't do any. So it's just one more problem and then a whole bunch of definitions. Okay, so let's add one more thing here. Oh, I need to copy this so I know what it is. Okay. Copy. Let's add. Right rule, I guess. Oh, I didn't want to add it there. It doesn't matter. I'll have to come up afterwards to do that. Okay, so. Oops. There. Okay, so let's do this. Make it a little bigger. So problem 32. Limit as x approaches 2 of x cubed is equal to 8. So let's do this. So again, we start out the same exact way. So this is a template. You always start out the same way. So you should not have any problem starting out the proof, any of these epsilon delta proofs, because they're always the same. So it's not like you have to be in any way inventive. It is something that you memorize, and it's not a lot of words to memorize. And then the rest of it's algebra. So you just remember this template, you follow your nose using algebra, and then you're done. So given epsilon greater than 0, let delta, I don't know what delta is. Let delta be something, which is greater than 0. Oh, by the way, now after I said all that, did I actually write greater than 0 here? Well, let me just say, oh, I did write greater than 0. Okay. I just wanted to be sure that I wrote greater than 0. I'm being paranoid. Yeah, I wrote greater than 0 everywhere. Yeah, okay. I was just trying to be sure that I didn't forget to write epsilon greater than 0. Delta greater than 0, sorry. Delta greater than 0 somewhere. It's hard to know where to put, how much space to put here, but this seems okay. So such that absolute value of x minus a, in this case is 2. Being less than, well, whatever it has to be, implies that, well, this x cubed minus 8 is 0. So let me put in some spaces here. I don't know, let's say here. It's kind of hard to figure out how much space to leave blank, but this is probably enough. I might actually need a little bit more space here. Just in case. Okay, so just in case I need a little bit more space. Well, what did we do in the last instance? We simplified And part of the simplification was factoring. So let's factor. Okay, so let me factor this. So this is the difference of cubes. So let me oops. So let me factor here. X minus 2 times x squared plus 2x plus 2 squared, 4. So I'm just using the difference of cubes formula that you remember from elementary algebra, math 115, or from junior high. Okay, so this is equal to, well, by the properties of absolute value. This is just the absolute value of x minus 2. Oh, and maybe I'll make, oops, make this a less than or equal to. I'll use a triangle inequality. So less than or equal to. And let me take the absolute value inside here. So this is less than or equal to. The absolute value of x squared plus absolute value of 2, which is 2, absolute value of x, plus absolute value of 4, which is 4. Oh, and I don't need the absolute value there since I take the absolute value of each of these. So let me write this as a parentheses, just to make it look nicer. Okay, so I need some bound. Oh. Yeah, that would have been harder. So I need some bound on x. Okay, so somehow I want a bound on x. Notice that writing it, I could do it as a bound on x minus 2, absolute value of x minus 2. Let's do it that way. Let me show you how to do it that way. So let me show you how to do it that way. So this is equal to x minus 2 in absolute value plus times, well, x is just x minus 2 plus 2. X is just x minus 2 plus 2. So all I've done here is I've added and subtracted 2. So let's do the triangle inequality. So x minus 2 times, well, the triangle inequality, this is less than or equal to absolute value of x minus 2 plus 2 squared. And this is less than or equal to absolute value of x minus 2 plus 2. Okay. Please note that for positive quantities, a quadratic function is an increasing function. So that's why this inequality holds. So if I could bound x minus 2 by something, let's say by 1. So this says that x minus 2 in absolute value is less than 1. And so I have that this is less than 1. Okay. So this is less than 1 plus 2 squared, 2 times 1 plus 2 plus 4. Okay. Notice that the linear function f of x equaling x and the quadratic f of x equaling x squared are monotone increasing for positive values of x. Okay, good. So let's simplify this. 1 plus 2 is 9, plus 4 is 13. 3 plus, no, well, let's do it this way. 3 plus 3 times 2 is 6, plus 4 is 10, plus 9 is 19. So if I could bound this by epsilon over 19, then everything would be nice and I would be done. So all I need do here is add epsilon over 19. Oops. Epsilon over 19, which of course is greater than 0. So and being less than delta implies that x minus 2 is less than epsilon over 19. And so I'm done. Any questions about this? I'm sure I did it slightly differently, but actually equivalently. So I did it slightly differently, but in an equivalent fashion, I think previously. Any questions about this? Okay, so lastly, let me try to give you the limits at infinity. So they give you, actually, I think in this book, they do give limits at infinity, but it's not till like chapter 3. I think they wait to chapter 3. And by that time, everyone has forgotten what limits are. So I'm going to give you the definitions here for infinities because it's a more logical place. So limit as x goes to negative infinity. So I have here some function. And I want to see what happens as x goes to negative infinity. If I can be as close as I wish to L by taking values of x that are sufficiently small, meaning that I keep getting closer and closer to this L, then we say that the limit as x approaches negative infinity of f of x is L. So let's do this in terms of epsilons. And well, not quite m. We don't quite call it delta, but it's equivalent to delta. We call it m. So we call this m. The limit as x approaches negative infinity of f of x is equal to L means the following. For every epsilon greater than 0, we're in this epsilon tolerance of L in this strip here. I want all of my y values to be in this strip. There exists some m, arbitrary m, less than 0, such that if x is less than m, so everything here, all x values here less than m, we have that f of x minus L in absolute value is less than epsilon, that you're within epsilon of L, meaning that you're in this strip. So if past M, you're always, all of your y values lie in this strip here, this epsilon tolerance of L. Then the limit as x approaches negative infinity of f of x is equal to this value L, because you are arbitrarily close to L for values of x that are sufficiently small. So let me give you a theorem. Oh, I didn't give you the positive infinity, which is probably because positive infinity is here. Oh, okay, sorry about that. Here's my positive infinity. It's the same idea. So let's take the limit as x approaches positive infinity. Well, if you can be arbitrary, if you're able to be if all the y values are arbitrarily close to L for x's being sufficiently large, then we say that y approaches L as x goes to positive infinity. So the limit as x approaches infinity of f of x is equal to L means the following. For every epsilon greater than 0, there exists an m greater than 0, such that if x is greater than m, then f of x minus L in absolute value is less than epsilon. So we can be arbitrarily close to L by taking x's sufficiently large. So for all sufficiently large x's, my y values are within that specified epsilon tolerance of L. Okay. So now, let me give you that theorem. Suppose k is greater than 0 and c is some real number. Then the limit as x approaches infinity of c over x to the k is 0. So if you have some bounded number divided by something that becomes gigantic, 5 divided by 100 billion is tiny, it goes to 0. Next, the limit as x approaches negative infinity of c over x to the k is also 0. So long as you're not taking even roots of negative numbers. So I don't want to take the square root of a negative number. So unfortunately over here, I might have some, obviously I have negative numbers, I'm going to negative infinity. So since my x's are negative, I don't want to take an even root of a negative number. So this is actually only true if k is equal to p over q, some rational number, where p is a natural number, well, where p is a natural number and q is a natural number, and where p over q is a reduced fraction, there's no common factors other than 1, and where q here is odd, meaning I don't want to take an even root. So I want that this root, this index here, I'm dividing by q, so this is the index of my root. I want the index of my root to be odd because I don't want to take even roots of negative numbers. Otherwise, I get a complex number. So modulo that little fact that, you know, you don't want to take even roots of negative numbers, then a number, rounded number, divided by x to some positive power, that will always go to 0 because you have some quantity divided by something big. Now, it could be big in the negative sense or in the positive sense, but it's big. So, you know, 2 divided by 100 billion is very close to 0. 2 divided by negative 100 billion is again very, very close to 0. So let's show this. This should all look very familiar. Given epsilon greater than 0, let m equal absolute value of c plus 1 divided by epsilon, all to the 1 over k, that's greater than 0. Then x being greater than m implies, please note, as always, this m here, or delta, cannot depend on x. It depends on, it could depend on epsilon, could depend on other things here, such as the c, but it cannot depend on x. So your delta, your m, cannot depend on x. If x is greater than m, then, well, m is equal to this, so x is greater than absolute value c plus 1 over epsilon, all to the power 1 over k. Therefore, I want to show that these are equal. So I'll subtract them and then take their absolute value. So let's take c over x to the k minus 0 in absolute value. Well, obviously subtracting 0 doesn't do anything. So this is equal to the absolute value of c divided by the absolute value of x to the k. But this is less than, well, x to the, so this is greater than 0. So this is, so the absolute value of x is greater than absolute value of c plus 1 over epsilon to the 1 over k. And so absolute value of x to the k is greater than or equal to absolute value of c plus 1 over epsilon. So 1 over the absolute value of x to the k is, oh, I see, I put it in here. Okay, is going to be less than 1 over absolute value of c plus 1. Or I just plugged it in, so the k's cancel. So you have here, this is less than epsilon over absolute value c plus divided by absolute value c plus 1. But I know that this quantity here is less than 1 for all real numbers c. And therefore, this is less than epsilon. And that's what you wanted to prove. Let's do the exact same thing for the second part. Given epsilon greater than 0, let m equal a negative absolute value of c plus 1 over epsilon, all to the 1 over k, which will be, of course, less than 0. The quantity here is greater than 0. You've negated it, so it's less than 0. So therefore, x is less than negative absolute value c plus 1 over epsilon to the all to the power 1 over k. So the absolute value of x is greater than, because you're taking absolute value. So it, the less than is a big less than. So the absolute value of x is greater than absolute value c plus 1 over epsilon to the 1 over k. Therefore, proceeding as we did it in the first part, c over x to the k minus 0 in absolute value is, well, absolute value of c over the absolute value of x to the k, which is less than, using this fact, is less than absolute value of c over the absolute value of c plus 1 over epsilon to the power 1 over k to the power of k. Put these cancel. So you just get to the power 1. And so this is equal to epsilon times absolute value c over absolute value c plus 1. And so this is less than epsilon, and that's what you want to prove. Last, some more infinite limits. So suppose that we have, I didn't show you the picture. Suppose we have and let's say 8. And so we have this situation. As x approaches a, we go in the two-sided limit to plus infinity. So the limit as x approaches a of f of x is equal to plus infinity means for every m greater than 0, oops, maybe I'll put, there exists a delta. So this width here is delta. There exists some delta limit as x approaches a of f of x is infinity if for every m greater than 0, there exists a delta greater than 0, such that if x minus a in absolute values between 0 and delta, so we're in this little delta tolerance, this little deleted delta neighborhood of a, f of x is greater than m. So all my y values here are greater than m. Okay, good. Okay, let's do it from small. Okay, so now there. Oops. And it does whatever it does on the other side. Maybe it just sort of does that. Okay, so hopefully I did the right side. Okay, good. It's the left side of the limit. Okay. The limit as x approaches a from the left, f of x equals positive infinity, means for every m greater than 0, there exists a delta greater than 0, such that if negative delta is less than x minus a is less than 0, meaning you're in the left neighborhood of a, then f of x is greater than m. All your y values here are greater than m. Okay. And of course, you can do it from the other side, from a right side limit. The limit is x approaches a of f of x is equal to infinity. If I approach a from the right side limit, This means that for all m greater than 0, there exists a delta greater than 0, such that if x minus a is between 0 and delta, then f of x is greater than m. So notice that you're in the right deleted neighborhood of a. Next. So now, instead of going to positive infinity, you could instead go to maybe negative infinity. Okay, so let's do this. Oh. I did that one. The limit as x approaches a of f of x is equal to negative infinity. If for every m less than 0, there exists a delta greater than 0, such that x minus a, an absolute value between 0 and delta, implies f of x is less than m. Similarly, we can do it the left side limit and the right side limit. The limit as x approaches a of f of x equals negative infinity, if we approach a from the left side, means that for all m less than 0, there exists a delta greater than 0, such that negative delta less than x minus a less than 0 implies that f of x is less than m. You can also approach from the right side. Limit, so the right side of the limit, x approaching a, f of x equal negative infinity, means that for all m less than 0, there exists a delta greater than 0, such that x minus a between 0 and delta implies that f of x is less than m. You can go to infinity both in the x values and the y values. So both your x and y values could go off to infinity. So you just keep, here's your x and y axis here. You just keep increasing both in x and in y. The limit as x approaches infinity of f of x is equal to positive infinity means that for every m greater than 0, there exists a delta greater than 0, such that x greater than m, oh wait, I think I said epsilons and deltas. Sorry, I think I said epsilon, I'm supposed to call it m's and n's. So let me start over again. The limit as x approaches infinity of f of x is equal to infinity means that for all m greater than 0, there exists an n greater than 0, such that x greater than n implies that f of x is greater than m. And well, you can go to plus infinity as you approach, as your x's go to minus infinity. The limit as x approaches negative infinity of f of x is equal to positive infinity means for every m, for every m greater than 0, there exists an n less than 0, such that x less than n implies that f of x is greater than m. Lastly, as your x's get larger and larger, your y's could get smaller and smaller. So as x goes to infinity, your y values could go to negative infinity. The limit as x approaches infinity of f of x is equal to negative infinity means for every m less than 0, there exists an n greater than 0, such that x greater than m, such that x greater than n implies that f of x is less than m. Lastly, your x values could go to negative infinity, and your y values could also go to negative infinity. The limit as x approaches negative infinity of f of x is equal to negative infinity. Means for every m less than 0, there exists an n less than 0 such that x less than n implies that f of x is less than m.